Hi everyone, can you please confirm if I'm audible? Okay, just let me know if you can hear me and then we can start. Cool. Hi Gautam. Hello Ashish. Okay, I hope things are good. Sorry for little delay and sorry I have shifted it, I scheduled it for 9 a.m. but I have to shift it 2-3 hours later because I was not feeling well. But now I think we can do it, right? Okay, let me know if everything is good. Hello Arpan. Now, today we are going to solve some of the very interesting questions that we have put in AIMT2. I hope that you have gone through the questions. Now you know that where are the mistakes that you have done. Let me know if you feel the questions are good or if you feel that they were lengthy or what are your thoughts on AIMT2 questions. So quickly let me know what are your thoughts on AIMT questions. Were questions too lengthy, or you later when you saw the concepts, when you saw the explanation, then you found out okay the question could have been solved within the time? What do you think? Or the questions are conceptual, or the questions are just typical questions? Let me know what do you think for AMT2 questions. So today we will be solving most of the questions of my subjects, which is like C programming, data structures, algorithm, engineering mathematics, and computer networks, operating systems, compiler design, like that, right? So we will be solving questions related to that. Cool. Let's just get started. And first question, let's just solve for this computer organization question. So what this question is saying, this is saying that there is an array that is X, which is of two rows and 128 columns, right? This is the dimension of array that is given to us, dimension of array. So I might not speak too loud because I'm having a throat problem. Like there is some, I'm having little bit of cough and cold. So I might not speak too loud, but I hope that is fine to everyone. I will just convey whatever the underlying concepts. I will just do a great analysis for every question, but I will not just speak too loud. That's the only problem with me today. Okay, cool. Harish is saying that good questions, little tricky. Arpan is saying that Samaj Gate. Chiranjeev is saying, sir, the questions are good but time consuming. Okay. Sri Ram is saying that Suprabhat. Okay. Hello, Sri Ram. So let's just continue. Now, what I'm saying that you have an array that is having 2 into 120 dimension, which means there are two rows and 120 columns. See, this is a question which is relating to cache miss rate, or which is relating to cache, and they have given the array in this question. Now, to deal with this kind of question, what we first need to do, see, let me just tell you that type of question that they ask in CAS is basically different type of question. We will just conduct a marathon in 2-3 days where I will be covering all the type of questions. But this particular type of questions basically is dealing with loop plus array, and then they are asking for cache miss rate or cache hit rate. That is what they are asking. So if it is dealing with loop plus array, then generally what happens, let's suppose this is a cache that you have. Now in this cache, what you need to do, you need to store the array, right? You need to store the array, store array. Now let's suppose that they say that you are accessing the array elements again and again, like one element you are accessing again and again. Then what will happen? Let's suppose you are this is your cache, and if you are storing the array, then let's suppose that you have stored x0, the first element, maybe x00 is first element here, and maybe not just x00, let's suppose these are the lines, maybe you have stored 4 elements here. Okay, I mean this size is too good enough to store the 4 elements of the array from x00 to, let's suppose, x03, something like this, right? Let's suppose this is big enough to store 4 elements. Now what you will do, you will be keep on storing array elements, maybe x1 or something like this, right? Or maybe you will be keep on storing the array elements in the array, in the cache. Then what will happen, if let's suppose you are accessing, you have stored x0 here. Okay, let me just say x0 you have stored here. So let's suppose this is the one dimension array that you have, and cache is such that you are storing, let's suppose, x0 here. Now, there are two things that they will be asking in the array type of questions. One is that they will be talking about the temporal locality, and they will be talking about the spatial locality. What is temporal locality? Temporal locality is, which means you are accessing the same element again and again, accessing same element again, same element again in future, right? In near future, basically. This is called temporal locality. What is spatial locality? It is basically saying that you access access nearby element, right? So what will happen if this is the case that is given to you? Then they will say that okay, just store the element. Let's suppose x0 you are having, you store the x0 somewhere, then you store x1 somewhere, right? And then let's suppose your cache is not big enough, or due to some constraint, let's suppose you come up again, and then you're storing x, let's suppose 14 here, and let's suppose the 16th element, which is x16, you have to again store at this position, which means let's suppose you are storing x15 or x16 something here, then you have to replace this, right? You have to replace this x0 if you have to store at the same location. Now what's going to happen, that next time you access this x0, there will be a problem, right? I mean, because the x0 has been replaced. So basically, if the same slot is given to multiple array elements, the same slot is given to multiple array elements, then the accessing again, right, accessing the same element again in near future will create a problem. And that's where the temporal locality come in picture. Like we will see the question, we will see how to solve those questions, and this is the particular question that we'll be solving today. And no, not just this question, like basically I will be solving 2-3 gate questions along with that, and then I will be just telling you, let me just go through that slide. I will be also telling you some more variations of the question. So basically we will not just solve you one question. So this is the one question that they have asked in the AIMT. We have asked this question, but we will not just solve one question, we will solve many of these variations, so that you will get more comfortable in these kind of questions, right, when the cache and loop is given. So these kind of questions we will definitely be solving in the marathon. I will take a marathon for the cache itself, okay, and Deepak will take a marathon for pipeline. And then we have also planned a marathon for floating point and DMA. So these are the basically 3 sessions that we will be taking of 2 to 3 hours each. Here in this case, we have in GATE, we have 65 PYQs, and I will try to solve all the PYQs which are relevant, and obviously I will be covering all the variations and all the basically different type of questions that they have asked in cache. Okay. So for this question, I will be just taking different variations so that you get more comfortability. But when the marathon starts, then also you will get to understand the cache crystal clear, that how they are dealing with the cache thing. Okay. Good. No, Arpan is saying that they have asked this kind of question in GATE 2007. Not just in GATE 2007, they have asked it many times. I mean, not just one times or 2 times. Okay. Good. Let's just get started. Now, I'm saying that here they will say that cache is given, and then they will store this element somewhere in the cache. Then if you are accessing, let's suppose x15, let's suppose if it is mapping to the same element, same slot, then it might be a problem to x0 if you are accessing the x0 again. For example, let me just ask you one example. Okay, let me just ask you one question. Suppose this is the cache that you have, okay, and then you put x0 here. Then you keep on putting till x14, you keep on putting. Let's suppose these are the 15 elements or 16 elements, maybe let's suppose these are the 16 elements you put. Okay, this is x15, these are the 16 elements you put here. Now tell me, if this is cache that you have, tell me, will there be a problem if you just access x0 to x15 once? I mean, problem, or let me just say that will there be a benefit? No, right? I mean, if you access x0, you have to store it here. If you access x1, you have to, let's suppose, store it here. But if you access them twice, I mean, if you access, let's suppose, one more time, then there will be a benefit of the cache, right? So this is the clear benefit of the temporal locality. When you are accessing same element again, temporal locality. So suppose that you store this x0 here, and then you access this x1, then you again have to, let's suppose, fetch this x1, and then you are storing it here. Then if you are accessing one time, then, and let's suppose each element you are storing at the different block, okay, something like this. So basically at that in this situation, this temporal locality, which means the same element again accessing, will not be much. This temporal locality is not there. But if you access the same element again, then you will not be missing on x0, then you will be hitting on x0, right? So this is one example. Let's suppose another example where in one block, generally it is an example of the real world. When in one block you are storing more than one element. Let's suppose x0 to x3. There are four array elements you are going to store here. Now suppose your array elements look like this. Suppose there is a for loop. Okay, there is a for loop, and in which you are accessing your array elements, which means I equal to 0, I less than n, I plus plus, right? I plus plus. Suppose you are accessing the array element again, and you are just doing sum equal to sum of sum plus equal to maybe sum plus equal to x of I, something like this you are doing, right? I hope you are understanding. Let me just write it clearly. Sum plus equal to x of I, sum plus equal to x of I, something like this you are doing. Now what will happen, you will store, so like you will first access this x of 0, you will store this x of 0 in one of the line, this is the line 1, let's suppose. But not just x of 0, when you are accessing x of 0, you will also access you will also store x of 1 till x of 3. So what is the benefit of it? Whenever you are accessing x of 1 in the near future, which is just next, then you will be missing, not be missing on x of 1, you will be hitting on x of 1, right? Have you understood this, what I'm saying? Okay. Sumant is asking, sir, when is the eigenvalue and eigenvalue marathon for the engineering mathematics? That particular video for the eigenvalue I have added in the playlist, so we will not be taking the marathon because we have taken it earlier. That's why we will not be taking the marathon for the engineering mathematics for the particularly eigenvectors and eigenvalue. But I will focus on the probability today. So today, most probably, like if my health is well, most probably we will be conducting a marathon for probability from 8 p.m. Okay, cool. Let's just see this question and let's try to solve this question. What they are saying is that they are saying there is one array which is having this dimension, and then you are accessing this array like this, right? Now first just see that how does this array basically look like in the memory. So let me just tell you, this is a two-dimension array. How does it look like in the memory? Like memory is flat, right? I mean generally you say that these are the two rows and 128 columns. That's fine, I mean that is good, but these are the two rows, this is 0th row, so this is x0 and this is x1, right? I mean anything that start with x0 will be in this row, anything that start with x1 will be in this row. For example, if you take x01, then this is the element which is saying x01. If you say x12 or something like this, 0 1 2 3, if you say x13, then this is the element which is x13. But this is the high level view. Let's just see that how does array look like in memory. See, array will always be flat, right? So this is an array which is two-dimension array, but in the memory it will be just like a flat array. So in the memory it will look like this, right? Now this is x0, this is x1. Now what they are saying, that they want to access some of the elements of this array. So the first step that you need to do, okay, I am not asking you to remember the step, but the first thing that you need to do is see how array looks in memory. Now just see that how many elements are there in x0. Every of this one dimension array is having basically 128 elements, right? Every of this one dimension array. Cool. So how many elements are there? 128 elements. So here, let me just write here 128 elements or integer, whatever you want to say. Let me just say integer, right? Now, because every integer is of 4 bytes that is given to us, so let me just also write in terms of bytes. So this particular block which is just having x0, it is basically 120 into 4 bytes, right? Now let's look at how does our cache look like. So this is the array in the memory. Okay, this is our first step that we have done. So this is the first thing that we have done, which is like we are just seeing that how does the array in the memory look like. Now what we need to do, we need to basically check that how does cache look like. So this is I will just put it side by side, that how this is how array looks like and this is how cache looks like, right? I mean cache will look like this. So this is cache. Now let's just see the cache parameters. They have given that cache is of size 512 bytes, right? And block size is 16 bytes. So it is basically 2 power 9 bytes. Block size is 16 bytes. That's why number of blocks here, number of blocks is 2 power 9 upon 16, which is 2 power 4. It is 2 power 5, which is 32 blocks, right? Number of blocks are 32. Basically, there are 32 blocks here. Each block can hold 2 power 4 bytes. And instead of bytes, let me tell you that how many integers it can hold, because anyway I'm bringing to the integers. So instead of playing with the bytes, let me not worry about the bytes and all anywhere, because I'm dealing with the integers here, right? No, not with the bytes. So it is better to deal with the integers. So I will say it is 128 integers, and each cache array block can contain how many integers? It can contain since it is basically 2 power 4 bytes, which is 16 bytes. Each is 4 bytes, so it can contain 4 integers. Right? Is this clear to everyone? That I have said like it can contain 4 integers. I have said like it can because of the block size it can contain 4 integers, and there are such 32 blocks. So if you want, you can start the mapping. I mean, just for sake of understanding, you can say 0 to 31, or maybe 1 to 32, does not matter, just for the sake of understanding. Otherwise, it is 0 to 31, right? So let me maybe write just 0 to 31 if you are okay with that, right? So these are the block numbers. So it is block number 0, it is block number 31, right? So is this clear to everyone? First we are looking that how does array look like in memory. Then we are seeing that how does cache look like. And cache is looking like this. This is the block number 0, this is the block number 31. And every block can hold 4 integers, right? Great. So I hope that is fine to everyone. So this is how cache look like, this is how array look like. Now we will go to the actual code that, okay, this is array, this is cache. How we are bringing the elements from the array to the cache. So this is how the actual code look like. So that's why I'm just copying this actual code there in that slide. Okay. Before that, let me know if you have any confusion, or there is some doubt, or otherwise I can continue. Yes, Charanji, we will tell you the random variable in such a way that you will actually understand random variable and you will never forget what is a random variable. Okay. So let's just do one thing. Let's just see that how we are bringing the elements, okay, which is in the main memory and to the cache. So these are the cache, these are the array elements. How we are bringing these elements into the cache. Is this clear that how does the array look like? How does the cache look like? Cool. Now what we are saying, how we are accessing is that basically we are accessing x00 into x10 first. So we are saying x00. First we are accessing x00 probably, and then we are accessing x10. Can you see some problem with this? So basically we are saying we are accessing, this is x00, right? I mean anything with start with x0, it is basically here and it is 0. So that's why this is x00, this is x10. These are the two elements we are accessing in the first iteration, right? These are the two elements. Now can you see the problem here? I mean, generally, it might not be a problem in general, but here it is a problem. Why? Because, see, what I'm doing, there is a memory that is given to me. This is the memory. And what I'm doing, I'm instead of accessing the memory sequentially, which actually better to me, right? Generally, it is better. Why it is better, you will get to know because of the special locality. So basically, instead of accessing it sequentially here and there, like sequentially, like this, what I'm doing, I'm basically accessing two elements, one from here, one from here. Randomly I'm accessing one from here, one from here. This might lead to a problem. We will see what is the problem that it is getting, but I hope that is clear that it is leading to the problem, because let's suppose this is my memory. If I'm accessing sequentially, then it is good. Otherwise, if I'm accessing like that, so something here, something here, something here, something here, something here, it might be a problem to me, right? Let's just see if it is a problem here. So I hope you are convinced that what we are going to do, right? So we have shown you how does the array look like. We have shown you how does the cache look like. Now I want to just check that how we are bringing the elements. So first we are bringing this element. See, these are the 128 integers. Do you agree? Now since these are the 128 integers, that's why can you tell me that how many blocks these integers will come? Number of blocks will be basically, each block can have 4 integers, right? So basically I think these are the 32 blocks. This will eat up the 32 blocks. Again, this will eat up the 32 blocks, right? So till now, I'm just having all the things in the place. I'm just saying that okay, this is how array look like. This is how cache look like, and this will take 32 blocks. This will take 32 blocks. Now, good thing. Just listen here carefully. Good thing about this cache is that, I mean, either it is direct map, set associative, or whatever, right? Good thing about this cache is that you can basically do one thing. You can use the mod operation, isn't it? Which means that you do not need to deal with the cache in these kind of questions until and unless they ask you to explicitly deal with the binary. You don't have to deal with the binary. Okay, so you don't have to deal with the binary. Now, I will not convert array addresses to the binary, and I will not check the binary. Why? Because I can do this question in the decimal format. How? I will say that okay, the cache is basically mod j. I mean, let's suppose these are this is your direct map cache. Let's suppose this is your direct map cache, and and if let's suppose number of the blocks here is you can take anything. Let's suppose these are the n blocks you have. Number of the blocks are, let's suppose, n. Then what I want to know, I want to know that if something, okay, maybe let's suppose this is the main memory that I have. This is the main memory. This is the cache. Now Just listen here, very important, very interesting thing, and that will make your life simple in terms of these questions. Okay, so suppose this is the block that you have. This is the block. Okay, block number could be anything. I'm not worried about the block number. This is the block. Obviously, there are more blocks than in the main memory than in the cache, right? Obviously, right? Because main memory is bigger. So these are the blocks that I have. Now suppose I'm using the direct map. Suppose I'm not giving the block number. I'm not giving the block number here, or neither I'm giving the block number here. Okay. Suppose this block is getting mapped here. I don't know the block number. Could be 5. It could be, it will be basically 5 mod n, right? It will be 5 mod n. It could be 5. I mean, whatever the block number here, what you will do, you will basically take a mod and then you will check that where it is mapping, isn't it? That's what you will do. So you will take the block number, you will do the mod operation, then you will check that okay, where it is mapping. That's what the direct map does. If you are using the cache set associative, then it is taking a block and then it is taking the mod of not the block number. Here I am writing the block number, but in case of set associative, you will not take a mod of the block number. You will take the mod of set number. I mean, sorry, this is not the block number. This is the number of blocks. Okay, total number of blocks in cache. And if it is a set associative, you will say total number of set in cache. So this is total number of blocks in cache. Okay. If we talk about set associative, it will be total number of set in cache. So anyway, I will go to the question. I will tell you the question. But before that, I want to make this understanding very clear. If you have the block number, you just take the mod. You will go here. Let me know if that is clear to everyone. That is obvious, but we will be using this kind of things to solve our question. Okay. So I hope that is clear. Now, interestingly, if this is mapping here, let's not even worry about whether how we are coming up with this 5 mod n or not. Okay, let's not worry about this. Let's not worry about that. What is the exact block number? But suppose I'm saying that you are mapping your this main memory block to here. So if I ask you, where are you going to map this? Then without even hesitation or without not doing anything, what you can say, you will map this to the next block only. Next block only. You will map this to the next block only. Why? Because how you have mapped earlier using the mod, you will also map using the mod. So if earlier was 5 mod n, and then you got this, let's suppose whatever the block number, then it will be definitely the next block, which is 6, right? So 5 plus 1 mod n it will be, which will be just a plus one to whatever I did earlier. So what I'm saying, that wherever you are mapping this in the cache, the next block will get mapped to the consecutive location only in the cache. Okay, this is quite interesting, quite important to understand that yes, this happens. Cool. Now let me go to one step further. Now let's suppose that I'm mapping, as I told you that all the mappings are contiguous because of the mod operation that I'm doing. Now let's suppose I'm mapping the next block. Then can you tell me that where does this next block map to? Where does this next block map to? This will map to here. Now where does this next block map to? Where does this block map to? Then you will say that this block map to the next location, which is here. Let's suppose this is the last block in the cache. Now interestingly, can you tell me, okay, let's suppose these are the only cache block that I have. These are the only cache block. This is how my cache look like, suppose. Now interestingly, can you tell me where does this the next block in the main memory map to? If these 4 blocks are mapping to the consecutive location, obviously they have to map to the consecutive location. Then where does this map to in the cache? This block. Let me know. This will map to. Can anyone tell me quickly? This will map to the next location. Since the next location is not there in the cache, so it will wrap around and it will map to the first cache. First block, right? It will map to the first block. So that's how you can do your mapping. I hope that is clear to everyone. So basically, like these all get consecutive. Once it is over, it will just wrap around. Now there has been a gate p by q, and I will also solve that in the marathon. But for now, tell me if there is a main memory. There is a main memory, and instead of there is a cache. Let's suppose I pick a random block here and it is mapping to some block which is here. Okay, maybe some random block which is this. Suppose this block is mapping to this. The random block I picked it here. I took the mod operation, okay, because that's how we find out the block number in the cache. I will take the mod operation. I'm saying that this is getting mapped to this particular line. Now, what will happen? The next block will map to this, the next block will map to this, and the next block will map where? Now tell me, the next block will map where? If this is the block number 0, 1, 2, 3, 4. Now the next block will map to which block in the cache? Can you tell me? I picked the random block, it is mapping to block number 2. I picked this block number 3, block number 4. Now tell me, where does this map to? This will map to, again, this will map to the 0th block. It will not map to, obviously, it will not map here. Why it will map here? I just picked the random block. So it will just wrap around and it will map to the 0th block. Okay. So basically, you have to wrap around. That's the only point I want to convey here. Now, let's just solve one gate PYQ, which is also very easy, and then we will be solving our question. So this is the PYQ that they have asked in 1999. What they are saying, the main memory computer has 2 CM blocks. So number of blocks they have given are 2 CM, while the cache has 2C blocks. So number of blocks in main memory, basically, right? Number of blocks in main memory they have given. Now, what we are saying, now I want to find out number of blocks. I mean, they have also given number of blocks in cache, which is 2C blocks. Okay, that's something interesting. So see here, they are saying there is a main memory which is having some blocks. Let's suppose 2 CM blocks, right? And here you are having a cache. Which is having some blocks, and this is main memory. This is a cache which is having some blocks. Let's suppose they have given it to 2C blocks. Number of blocks they have given. Now tell me, if you pick this block, let's suppose this block is mapping to this block. Now how many of the blocks from the main memory will map to this particular block? Maybe any block number, but I'm saying let's suppose block number 0. So my question is that how many of main memory blocks will map to cache block 0? Let me know. What do you think? How many will map to cache block number 0? So see, here it is 2 CM blocks, which, and this is just 2C blocks. So basically main memory is m times more than cache block, right? M times more than cache size. So each block here will accommodate, each block will accommodate. Accommodate means like it will get mapped to m blocks in the main memory, right? M blocks somewhere. So m blocks in the main memory will map here. So number of blocks which map to the particular any block, okay? M number of blocks. Because this is m times greater. If it is m times greater, then it is m number of blocks which will map to the particular slot in the main memory. So it will map to this particular will map to m, this particular map to m, this particular will map to m, and total this is 2C blocks. So total it will be accommodating 2C into m, 2C into m blocks, which is 2CM blocks. I mean, it will be like cache has to map to the main memory, right? So that's why you will be accommodating 2CM blocks in the cache, not at the same time, but at the different time probably. Now suppose this is the block number J. If I'm saying, tell me numerically where does this J map to? Okay, have you understood my question? I'm asking that if this is the block number J, then what I'm asking is that where does, in which block number this J map to? Then you will say that you can just take J mod number of the blocks, right, in the cache. So J mod number of the blocks. Let's suppose the number of the blocks here is 2C blocks. So it will map to J mod 2C, isn't it? So it will map to J mod 2C. That's what they have asked. They have said if K is the block number, then it will map to which particular line in the cache. Then you will say K mod 2C is the answer. C is the correct answer. Right? Okay, sorry. This is not direct mapping. This is not direct mapping. 2C is the number of blocks. Now they are saying that this is set associative mapping with 2 blocks per set. Cool. I will come to it. But for now, let me know if that is understood. Okay, if this is direct mapping, then this particular will map to the number of blocks that you are having. You will be writing here. But now suppose that it is just set associative memory, which means there is a main memory and the cache is set associative. So now there is a cache which is having the same size, which is basically 2C blocks, and each set is having two lines. This is two lines. Tell me number of, sorry, two lines. Number of sets in cache. If there are 2C blocks, each 2 is making one set, then how many number of sets are there? These are the C sets, right? Because there's 2C blocks, each 2 block is making one set. So now if I ask you, let's suppose this is the block that you have, right? These are the two lines internally. These are the two lines basically. Okay, this is the set number 0. This is, let's suppose, set 0. Now if I ask you that where does this block to, this map to? If this is the block number k, then you will say that it will map to k mod number of the sets this time, which is C. Earlier it was mapping to number of the blocks, which was 2C. Now it is mapping to number of the sets, which is C, right? So k mod C is the answer. Now you will, if I just ask you to find out the answer, then you will say this is k mod C of the cache, because it is two-way set associative. Okay. Now coming back to our question, we are saying that we are having this kind of orientation, which is basically 32, 32. Now you know we don't have to deal with the binary, we can deal with just the mod, right? I mean, you can know, if given a cache line, you can know where does this map to. It is just mod of number of the sets or number of the blocks, right? I mean, if it is set associative, number of the sets. If it is direct map, number of the blocks. So this map to J mod n. Now this could be number of the sets or number of the blocks. It depends on if it is direct map or it is not direct map, right? I mean, this is set associative. Okay, cool. Now what we are saying, we are having these are the integers which span across 10 to 32 blocks. Now let's make this little interesting, and let me ask you a very simple question. If let's suppose I say, okay, so let me just remove this for now, just for a minute. So suppose I say that this is mapping, okay? So you pick one block here, which is basically the 4 integers. So let's suppose these are the 4 integers, 1 2 3 4. This is the one block, okay? Let's suppose this one block is mapping here. Is this okay to everyone? Suppose, assume that this one block is mapping here. Now how many blocks are here? 32 blocks. So the last block, which is this, right? Last block, which is also having the 4 integers, will map to this, isn't it? Because everything is sequential. That's what you need to understand. If this block is mapping here, then the next block will map to the next, and the next block will map to the next. So everything is sequential because of the mod operation. You don't have to deal with the binary. That's what I'm again and again saying. Basically, for this question particularly, you don't have to deal with the binary, because you know that this, wherever it is mapping to, the next will map to the next immediate location, right? Immediate block number, next block. So these are the 32. So it will map to the last one. Now, if it is mapping to the last one, now tell me, where does this map to? Tell me, this is the, let's suppose, the block, okay, which is having the 4 integers. Where does this map to? Can anyone tell me the block number? In the cache, where does this map to? I will be very happy if someone tell me the block number. See, you have to do sequential. If it is mapping first, and then since these are the 32 blocks, so all of this x0 will exhaust the 32 blocks, right? Now this will map to again the block number 0. This will again map to the block number 0. So that's what I'm asking. Yes, Harish, that is correct. This will again map to the block number 0. So that is why I will say that these two elements, these two blocks basically are mapping to the same block, right? I hope that is fine to everyone, that we are doing it using the decimal, not using the binary. So what I want in our code, I want to access this particular element and I want to access this particular element. So not I will be just shifting one block, just one element, I will be shifting the 4 elements, because one block is containing 4 elements. So when I access this particular block, this will be containing x0, x0 is default, and then x00 to x03. I will be basically shifting the 4 elements, isn't it? If I'm accessing one element, I will be actually shifting the 4 elements here. But for the first element, let's go step by step. I'm first accessing x00. For that, there will be definitely a miss which is called a compulsory miss, because first time whenever we access, this is called compulsory miss. So there will be a compulsory miss because of this particular element. Now tell me, whenever you are accessing this x10, since it is also mapping to the same location, and since it is also compulsory miss, won't it replace this particular set of elements that you are having the same block? Yes, right. So you are going to replace. So that's why it is going to contain x10 and x13. So what's going to happen? Let me just tell you. See, this is how your memory looks like. I mean the cache looks like. Let me just tell you that how does your cache look like. So at I equal to 0, right? At I equal to 0, you will be accessing x00 and x10. So after this, cache will look like this. First, you will be having x00 here till x03, definitely, right? And then you will be replacing this, because that map to the same location, that x10 also map to the same location. You will be replacing this with to x10 and some other elements, right? Which are the 4 total integers. Let me know if that is fine. So your memory, I mean the cache memory will look like this, which is having x10 currently, right? It will, this x00 unfortunately get replaced. Why I'm saying unfortunately? Because the moment you access the next element, let's suppose this is the next element that you are accessing. The moment you access the next element at I equal to 1, which is basically x01, and you are going to access x11. The moment you access x01, this you will say that okay, this x01 is not in the cache because the x10 has been replaced. This particular element will replace this particular block, right? So that's why for the x10 you will look in the cache, there is no element such that x10. So now this is basically the memory that you have got after t equal to, or I equal to 0. After I equal to 0, you got this memory. Now let me tell you at I equal to 1 how you are manipulating the memory. Now this x01 will replace this particular element, which is x10. X01 will replace this with some other elements, which is 4 other elements, right? Now what will happen? You are going to say that okay, this x10 has been replaced. Now you are again going to access x11. X11 you are going to access, but that is not in the memory. So you are again going to replace this x11. So basically you are accessing this, and then you are accessing this, and because of that, ultimately in your cache you have this element only. But then you access this, it is the compulsory miss that you have. I mean not the compulsory miss, sorry. This is like this particular has been replaced, this x these four integers. So that is why you will be again missing on that integer. So basically what is happening, you are having some array which is having four integers. One, I mean the set is having 4 integers, 1 2 3 4. The block is having 4 integers. So first you access these 4 integers, then you access this is 1 2, let's suppose 3 and 4, 1 2 3 4. Then you access these 4 elements. So first you access these 4 elements, then you access these 4 elements. So what will happen, these 4 elements will be there in the cache, but since these 4 and these 4 are mapping to the same block, so that is why once you put this, you are going to replace this by this, right? And then you are again going to access this element. Then there will be a miss. Then you are again going to access this element. Then there will be a miss, because because they both are mapping to the same cache block, right? So that's why for every element there is a miss. For every element there is a miss. That's why the miss rate is 100%. If you talk about the number of misses, can anyone tell me number of misses? Number of misses will be number of elements in the array, which is 2 into 120 misses. These are the number of misses, and total number of memory reference is also 2 into 128, because we are looping for 2 into, I mean we are looping for 128, and then each time I'm accessing 2 elements. So total memory reference is this, total misses is this. That's why there is a 100% miss rate, right? So Devanjan is asking, sir, when x01 is miss, then x01 into x01 to x05 fetch to the cache block 0. Not x01 to x05, x0. Okay, what are you saying? When x01 is missing. Okay. So No, it's not like that. See, this is basically not having element to element by element. This is having the block by block, which means this particular block will map to. Okay, this particular block is basically always whenever you access this or this, whatever element you access, this particular only this particular block. You will not say that you are starting from x01. So he is saying from x01 to x04 or x05, whatever, right? And will you bring into the cache? No, we will not bring this particular. This is the block, right? You have divided the blocks and then you are doing the things, right? It's not like that. If you are accessing this element, then from here the block will start. No, the block offset for this particular element is not always 0, right? I mean, this is the first block, then block offset is basically the one integer, which is the 4 bytes. Okay, cool. Now let's just do this little bit variations of this, and then I'm saying, let's suppose I'm saying that the cache is now direct map, the same cache, but I'm increasing the cache size, right? I'm saying that now the cache size has been increased, and not just increased, it has been doubled. So what I was earlier doing was like this, right? Now what I'm saying, keeping the block size same, I'm just increasing the cache size. Let's see. So now the miss rate is 100%. Let's see if it is helpful. So what I'm saying, that still the block size is same. So that's why these are the 32 blocks that I have, right? And then this is x0. Since the block size is same, that's why I'm not changing these 32 blocks. This is x1. These are the also 32 blocks. Okay. Now the cache is looking like somewhat different. So earlier these were just 32 blocks in the cache, but since the cache size has been doubled, so that's why these are the 64 blocks in the cache, right? 64 blocks in the cache. Now tell me what's going to happen. See, see what's going to happen now. If you are accessing this particular block, I mean not just x0, you can access any element which is x00 or x01 or something. If you are accessing something from here, then this is the first block which will map to the, let's suppose, the first block, okay, the first block here, which is perfectly fine, no problem. Now the next will map here, and then you know the sequence, right? I mean, this is always sequential, but the way we are accessing is this. We are mapping this here. Now tell me, if this is the block number 0 where it maps to, then tell me where does this particular block map to in the main memory? Where does this particular block map to? See, it is always mod number of blocks, or maybe you can use your intuition also. Can you tell me the block number? Where does this map to? It is going to be an interesting question, that where does this map to? Okay, so this will map to the block number 32, I think, right? Because this is going to eat up 32 blocks, which is 0 to 31 blocks. It will eat up. This will eat up 0 to 31 blocks, and now this will map to the block number 32, right? So this will map to the block number 32, which is maybe here. So these two are not mapping to the same location. But does this helpful to us? Let's just see. Now, at initial it is not helpful, but now you access the next element here, right? You access the next element here in the same block. But now you have not replaced it, so that's why for the next element there will be a hit, there will be a hit, there will be a hit. So out of 4 times, right? I mean, here you have accessed this four blocks. Out of 4 times you are getting only one miss and 3 hit, right? Now you will be accessing this element you have accessed, then you have brought this, then you will be accessing the next element, then it will be a hit, right? So for every four, there is just one miss. For every 4 access, there is just one miss. That's why the miss rate is 1 upon 4, which is 25%. If you are doubling the cache size, let me know if that is clear to everyone. Okay, cool. Now suppose interestingly, if I run this loop one more time, okay, not just once, maybe I write the same code here, or maybe it is in the inner loop. If I run this loop one more time, then tell me the miss rate in second run of the loop, second run of the tell me miss rate in the second run, not in the first run. In the first run it is 25% miss. Now in the second run, tell me what is going to be the miss rate. Yes, yes, it is 0%. Extremely nice. See, every element is already in the cache. Why? Because this block in the cache, which is mapping to block number 0, next block in the cache, block number 1, this block number 32, and last block is block number 63 or 64, whatever, right? So it is block number 63. So last block is also in the cache. So basically, every block is in the cache because my cache is big enough. So that's why miss rate in the next run of the loop will be 0%. That's called temporal locality, because you are accessing the same thing again, right? That's where the cache is helpful, right? Temporal locality. Okay, I hope you understood. Now let's take the previous question again. Let's take this previous question again, where I'm saying that this will get replaced and all. Now tell me, in the second run of the loop, in the second run, what is the miss rate? What is the miss rate? See, it is again the same, which is 25%. Sorry, 100%. It is again the same, which is 100%. Why? Because here in the cache, you will be storing, since you are accessing this, I mean, these two blocks, this block and this block. Let me just call this is one block. Okay, this is one block and this is one. Since these two blocks are mapping to the same location, you are keeping this at the final, right? I mean, because you are accessing later, then you are keeping this as the final, or vice versa, right? One of them will be final. Then since this is in the cache finally, and these two are mapping to the same location, similarly here in these two, you will be having this finally in the cache. So in the cache currently this x1 is present, right? In the cache currently this x1 is present. After the end of the first for loop, in the cache the x1 is present. Now if you access again, then since you are accessing this element first, then there will be 100% miss rate, right? Because have you understood that in the case after the one run of the loop, let me just write it here. After one run of the loop, so after one run of the loop, we have x1, complete x1 in cache. Okay, I hope that is fine to everyone. Now you have understood little bit that what we are doing, right? Cool. Now let's just solve more variations, as I said. I hope that variation is clear. This one. This variation is clear to everyone. Now what is the answer that we have got? 25%, right? Now do you want me to solve one more variation, or you can solve it? Maybe let me just do it for the set associative, right? How does the things behave in the set associative? So suppose this time I have everything same. Okay, I have everything same as earlier. I have everything same, but now it is two-way set associative. Cool. So everything is same. Now it is two-way set associative. So let me just see. So which means everything same means this is x0, which is having 32 blocks. I mean that will that will span across 32 blocks. This is x1, which will span across again 32 blocks. Suppose my cache is as per the initial first question, my cache is just a 32 blocks only. And now what I'm saying, that you are mapping this to the first block. Let's suppose this is the first block, you are mapping like that, right? I mean that's what the story that we have done earlier. Now what they are saying, now this time you just consider them as a two-way set associative, which means 16 sets. So like there are 32 blocks, but each block has been put into one set, and there are such 16 sets, right? So now tell me, instead of writing 32 blocks, what should I write? Maybe I can say 16 sets. Does this help us? Let me just think. Yeah. So basically, instead of saying 32 blocks, I am saying it is basically spanning across 16 sets. Okay, this is also spanning across 16 sets. Since this is also 16 sets, so what you will do, you will basically you will not shift a set. Obviously, you will always shift, even though it is spanned across the 16 sets. You will always shift one block. Okay, so this is, let's suppose, the first block. When you access this, since this is spanned across the 16 sets, this will map to here. And let's suppose this is the first set, or maybe you can talk in terms of line also, right? I mean, if you access x00, it will map to the first line. Now, if you access this particular element, this is also mapping to the first line, I mean the first set only, right? But since there are two lines in one side, that's why you do not need to replace. So what is happening here? The first line, whenever you access, that will map to this same set that you are mapping here, because it is again the mod operation. These are the 16 sets. So basically, this will map to the first set, right? This particular is basically having a less size, but that is okay. This particular line is having, let's suppose this is one line basically, or one block. This is mapping to. So how does the set associative behave? Let me just tell you. See, in the set associative, you are having 16 sets, right? Something like this. And in the main memory, I made it too big. So let's suppose this is cache, and in the main memory, I have many lines. This is the main memory. Now, just think in terms of line only. Okay, it is just a logical grouping of the set that we have done, but that is okay. So the first line, if the first line is mapping to the first set, so second line will map here. Let's suppose this is a set which is having the two lines, okay, which is having the two lines, that's okay, which is line number 0, line number 1. But in terms of set number, it is set number 0, it is set number 1. Now tell me, where does this map to? In which set this map to? This is a second line, okay, not the set. So what I'm saying here, it might be confusing at the first place, but it will be very clear. This is the set. This is, I'm talking in terms of line. Line number 0 is mapping to the set number 0. Where does this line number 1 map to? Where does this line number 1 map to? Let me know. Where does the line number 1 map to? See, here earlier what was happening, here and earlier story little different. You need to take the mod of set, right? Line number will map to the set number 1. This is interesting. Even though this is line, you again need to take the mod of set. So it will map to the set number 1. Line number 3 will map to the set number 2, right? I hope that is clear for the set associative. Now let's just compare this with the associative. So let's just compare this with the direct map. So in the direct map, what was happening? Okay, everything is same, but I just kept it direct map. Okay, let's suppose this is direct mapped. Now this line number 1 will be mapping to, okay, in case of direct map, these are the two lines here, right, and not the set. So basically these are not the set. You have the let's suppose these are the two lines, and everything is having two lines. I mean there is no set here, so everything is having two lines. This is two lines. So I hope you can see my pen color. I'm using a different color just for the sake of writing. So basically this is mapping to the line number 0. And then tell me, where does this line map to, or this block, or whatever you want to say, block or line. So where does this block 1 map to? Where does this block 1 map to? This will map to which line? Where does this map to? This will map to the line number 1. Line number 1. That is important. That will map to the line number 1. Okay. I hope that is fine to everyone. See, earlier and now I will just make it very clear, so that you do not have to struggle with these kind of questions in future. And I will take a marathon where I will be actually solving these kind of questions very clearly. But earlier I was saying this is mapped to the set number 0, this is mapped to the set number 1. Now I am saying this is line number 0 is mapping to the line number block number 0, line number 0, whatever you want to say, and then this block number 1 is mapping to the block number 1 again. Okay, is this clear everyone? Now what is happening here, this line, the main memory blocks are mapping to 0 and 1, right, in the line number. Now tell me, where does sorry, so in the set associative, I am saying this is the block number 0 which is mapping to the set number 1, right? This is the block number 0 which is mapping to the set number 1. Now what I am saying, where does this block number 1 map to? You are saying set number 1, which is right, Now tell me, where does this block 1 map to which line? I'm not asking about the set now, okay? It is a set associative, but I'm asking about the line. Tell me, where does this block 1 map to? In which line it map to? Not the set. It is a set associative. I'm not saying it is a direct map. It is a set associative. Now I'm asking the same question, that which line it map to? It's very nice question. Let me know in which line it mapped to. See, it will map to the set number 1, right? Which means that line number, this is line number 2 and line number 3. So it can map to 2 or 3. I mean 2 or 3, I mean it is mapping to both. So you can put it either in 2 or 3. So that's what set associative is doing. See, in the set associative, it is mapping to the first set, it is mapping to the next set, right? In the line, in the direct map, it is mapping the first and then the second. So I hope that is clear. So basically, let me tell you how does the set associative looks like. Set associative. So see, this will be your main memory, and this is, let's suppose, your cache. Now, let's suppose these are the 32 lines or maybe 16 sets here, okay? Whatever you want to call. Now, I'm talking about the set associative. This is the block number 1, which is mapping to the set number 1, and this is one set, okay? These two are one set. This is basically one set. 2 is making one set. Let's suppose these are the sets. It is mapping to the, in terms of line, it is mapping here. Now, interestingly, in terms of line, if I talk about, then it is mapping to, after skipping one line, it is mapping here. See, one line has been skipped here. Let me know if that is clear to everyone. Earlier, they were mapping to the contiguous line, but now one line may have been skipped because they are mapping to the contiguous what? Contiguous sets. Okay. I hope that is fine. Let me know if there is any confusion here. See, you should be very clear with the representation also. How pictorially you should be clear, not just just using the binary and all. You should be clear that okay, this is in terms of line or in terms of block. If I say it is mapping to the line number 1, block 0, or it is mapping to the line number 0, then block 1 will map to line number either 2 or 3. I'm not saying exactly 2, but either 2 or 3. So basically, you are skipping one line or maybe 2 lines if you are mapping here, just like that, right? So you are skipping here. You are skipping some lines here because you are mapping to set by set. And in case of direct map, you are not skipping line. In case of direct map, you are assigning to the contiguous lines. Is this clear to everyone? Okay. Now, let me know. See, if you do not let me know, and I am having a little bit of throat infection today, so I have to speak it loud, and then it might get worse if at the end of the lecture. I mean, my throat can completely be destroyed. Okay. So anyway, I hope you understood, and let me know if there is any doubt. Now let's come to the question. Here I am saying these are the two chunk of the memory, which is basically x0, x1. This is basically 32 blocks. This is also 32 blocks. Now let's just see that how you are mapping them. This is your, how does your main memory look like? Okay, how you are mapping them into the cache, where you are having 16 sets. You are having 16 sets. So this is one set. Okay, this is one set. This is another set. Now you will map to, let's suppose this is the first block. You will map the first block here in the first set, and then the second block in the next set, right? So basically, these are the 16 sets that you have, and then you will be mapping each of them to I mean, since there are 16 sets, then see, let's suppose this is the next block. This is the next block. You will mapping that to next set, right? You will mapping that to next set. That is okay. Okay. Just a second. This is 16 sets, which is 32 blocks, means 16 sets. That is okay. No, this is 16 sets. Yeah, so actually I'm just saying that how the mapping, I think that is clear, that this maps to the set number 0, then this maps to the next. Okay, this is the next block, will map to the next set, and this is the last block, will map to the last set. So the only thing which I'm currently seeing, that one side there are two blocks that it can hold, but let's suppose that I'm accessing this, then it will go to the first or first set where I can do anything. So these are the 32 blocks, these are also 32 blocks. So if you are storing this, then this cache should be completely full. Okay, but it seems not, it is not completely full. I mean, these are the 32 blocks, these are the 30 blocks, 32 blocks. So see, earlier what was happening? Earlier, this is, let's suppose x0, which is having 32 blocks, right? It is x0, and this is your cache. So the cache is also having 32 blocks, where you are going to map this to this block, you are going to map this to this block. This is the earlier, right? Indirect map. I will come to the way how we are accessing the memory, but earlier in direct map we used to do this. Now let's just see that how we are doing in the set associative. So in direct map I hope things are clear. Now let's just see how to do it in the set associative. So you will map this to this particular set, the first set, this to the next set, okay, and this to see. uh, okay, just see here that you are having here 32 blocks. So earlier is this clear that how we are mapping? Earlier is this clear how we are mapping? Okay. Now, if this is mapping to this set, this is mapping to the next set, then what's going to happen? That this will map to the next set, and just after the 16 blocks, right? Just after the 16 blocks, you will say that the things are done. I mean, this after the 16 blocks, this will map to the last 16th set, right? This will map to the last 16th set. So just after the 16 block, you will say that each one of you have assigned at least one block to each one of the set. So what you are doing, that it is basically having 32 blocks, and it is also having 32 blocks. Let's suppose, okay, it is also having 32. Now earlier I think things are clear that we are doing the direct mapping, which is like this, right? We are doing the direct mapping. So earlier it is clear that it will directly be mapped, something like this, right? So earlier I think things are clear. Now what we are doing, we are saying that here you have each I mean, you have the 16 sets here, right? So these are the 16 sets you have here. Now what you will do, you will map this particular line number 0 to one set, but it can actually hold two lines, which is perfectly fine. Now next line you will map into the next set, right? So basically, since these are 16 sets, so after just 16 lines, you will say, let's suppose this is the 16th line, you will say it is mapping to the last set, isn't it? Which is this. So basically you will map this to the first set, this next to the second set, but after just 16 line you will say that okay, this is you are mapping to the last set, which is this. Now what will happen to the next line, which is this? Where does this map to? In which set? Let me know. In which set is mapped to? This will be mapped to the set number 1 again. So basically the set number 1 will be having the line 0, and here you are having line 1, right? I mean, similarly till line 15 you will be having line 15. Then line 16 will again go to the same set. So basically it is not only containing line 0, it will also be containing line 16. This will contain line 1 and line 17. I mean, line 1 and line 17 will map here, right? Line 0 and line 16 will map here, something like this. Okay, so basically this you are going to the set number 0, then line 16, I mean after this these 32 blocks you will be basically exhausting your cache. So basically line 16 will also map to the same location, same set where the line 0 is mapping to. Now let's suppose you have the more blocks in the cache. Okay, not just 32 blocks. Now this time let's suppose these are the 64 blocks in the cache. But before that, let me know if that is fine to everyone. Okay, so Devananjan is saying, sir, got it. Main memory block 15 maps to the set 15. The main memory 16 will again map to the set 0. Yeah. So basically, now let me just extend this question. Now you are having 64 blocks then, and this is just 32 blocks. You are using the set associative. So this block number 0 will map to the set number 1 definitely, right? This block number 0 will map here the set number 1, because how many sets are there? These are 64 blocks. Okay, let me not worry about the number of sets here. These are the 32 blocks, which means 16 sets. Let me worry about the sets here. So basically this will map to the first set. Since these are just 16 sets, so that's why after just 16 lines you will exhaust, right? So this will map to, let's suppose this is map to the last set. Now what will happen to like line number 0 has mapped here. What will happen to the next line after the 16th line, which is line number 16? So line number 16 will also map here, right? And since after just one iteration, like you will say that line number 15 is mapping here, and then line number 31, okay, I mean you need to do plus 16, line number 31 is mapping here. So but basically here are the 64 blocks. Since here are the 64 blocks, these are the 32 blocks. So each line should hold how many blocks? I mean should be mapping, not hold, should be mapping to 2 blocks, right? So this block 0, or let me not talk about in terms of block, but in terms of set, line 0, line 16, and then line, you just add 16, line 32, and line, okay, line 0, 16, 0 will map here, 16 will map here in the set 0, line, and then line 48, yeah, 0, 16, 32 and 48. These 4 will map here. Why? You can do the mod operation. Line number 0, if you want to find out the set number, just do mod 16. Line number 16, mod 16. Line number 32, mod 16. Line number 48, mod 16, right? So basically these 4 lines will map to this set, but obviously it will be holding just 2 at a time, right? Okay, so how we are doing now? We are having these 64 blocks, and these are the 32 blocks that you have, or maybe 16 sets that you have. So each set will be containing 2 lines, and you can say here 4 of the blocks will map to, right? Not just 2, because I have the double size. So if 2 are mapping, if I have the occupancy of 2 and 2 are mapping, then it is basically the same size. Since I have double size, that's why the double should map. So basically 4 blocks should map here, right? So the first will map, this is the block number 0. This will map to the set number 1, set number 0, and the block number 0 will map, and then similarly the block number 16 will map, and then block number 32 will map, and then block number 48 will map, right? So these are the 4 blocks will map, block number 48, and then total I have 64 blocks. Okay, so I hope that is fine in case of two-way set associative. Now this is the block number 48. Now let's just do one thing. Let's just see that in our array how does it look like. So basically this is the area of x0, right? From block 0 to block 31 or something. So this is the area of x0, and rest is the area for x1. So block number 32, starting from block number 32, this is the area for x1. This is how in memory it looks like, right? I mean it is taking the 32 blocks, it is also taking the 32 blocks. Now let's just see that what's going to happen if I'm going to map it. So in the cache I will be containing the block 0, then I will be accessing this, that I will be mapping to same set, right? Because this is mod, right? 32 mod 16 is 0, and this block 0 mod 16 is also 0. So I will be mapping these two to the same set, but this time it can hold 2 at a time, so not a problem, right? It can hold x0 and x0 0 to x03 x0003, and similarly x01 x10 to x13. It can hold two blocks at a time. Now when I'm going to replace this, I'm going to replace this with the block number 0, block number 0 will map, 16 will map, 32 will map, and 48 will map. So first I'm accessing 0, then I'm accessing 32, okay, and then after some point in time I will be accessing 16, right? I will be accessing block number 16. So I will be replacing one of the block, maybe using the LRU, okay, maybe using the LRU. I will be replacing one of the block to block number 16. So let's talk in terms of block, okay. Let's talk in terms of block instead of the array elements. So let's suppose that I'm accessing the block number 0 at some point in time, and then I'm accessing at some point in time block number 32 after that, and then I'm accessing block number 16, then I will be accessing block number 48, okay. I mean my way of accessing is 0, 32, 16, and 48. I mean in this order I'm accessing, and then let's just see how does cache behave. So here I will be mapping all of these 4, right, in the set number 0. This is the set 0. I will be mapping all of this. So what I will do, I will map 0 here, then I'm accessing 32, then let's suppose I'm accessing 32, then I will map 32 here. But the moment I access 16, there will be a problem, right? So I will be replacing. I hope that is fine to everyone. And in the array, what we are doing, we are basically accessing x0i, and for I equal to 1 to 0 to 128, and then at the same time we are accessing x1i, right? Okay, so we are accessing x0i and x1i at the same time. I mean, just one after another. So these two will map to this. Okay, x1i is basically this particular block. X10 is this particular block is having x10. This particular block is having x00. I mean that is fine. Now in the next iteration, I will be accessing x0. It was the x00. I will be accessing x01 in the next iteration, right? Since x01 is already there, so it will not be a miss. It will be a hit. Similarly, I will be accessing x11 in the next station. It is already hit, and then I will access x02. It is already hit. Then I will access x12. It is already hit, right? So first I am accessing this. That I will keep 4 elements here. I will keep these 4 elements here. Now the way I am accessing from the main memory, basically I am accessing in this way. These are the 4 elements. So I'm just telling you for few iteration, like first maybe I can say 4 iteration, right? So in just first iteration, what I'm doing, I mean for I equal to 0, I'm accessing this, and then I'm accessing this. This is what I'm accessing for I equal to 0. And because of these two access, I will be putting both of them in the cache. Then for I equal to 1, I'm accessing this one and this one. This is already there. Then I'm accessing this one. This is already there. Then I'm accessing this one. This is already there. So basically I'm accessing 4 times and I'm just missing one, right? Let's just see if the pattern repeat. Now you will be accessing the next element. I mean you will be accessing this, and then you will be accessing this. So you will be mapping that to the same in the next set, and so on, right? And then since there are 64 blocks, but here are just 32 blocks. So what you will do, I mean this will map to the next set, but after just 16, maybe you can say this is the 16th number. The moment you access this 16th number, that will also map to the same set. So here yeah, so basically what will happen, for the first block, this is the compulsory miss, and then you are hitting on these 3. Now again this is a compulsory miss, you are hitting on these 3. Now here again it is a compulsory miss, and then it doesn't matter, you are mapping to the same you are mapping to the same set, it doesn't matter, but anyway it will be a compulsory miss. But since you are accessing this element and then this element, you are accessing this, and then again it will be a hit, right? So every 4 element is for every 4 element I'm just getting one miss, which is 1/4 miss rate, okay, which is 25%. So actually like that is what we will be doing in the marathon, but for now I'm just telling you that this is how the cache is looking like. Now just for the exercise purpose, what I'm saying here is that just do I mean this is the like 25% that we have gotten. Let me see the answer also. Yeah, see, this is the 25% that we have also gotten, right? Now Okay, this is 100, 25, 25. So these three questions we have done. These three questions we have done. Now we can do other variations also. We can do for these three questions. It is also two-way statistical system. Now let's just see if you can do it. Okay, we will be solving them in marathon, and let's just focus on the AIMT question currently. Let me know if you have understood this particular way of explanation. So actually, you do not need to worry about the binary. That's my point here. It took almost 1 hour just to explain this, but I hope that is clear because that is very important concept to understand in the cache. Okay. Now let's move to the next question. Let's see this question. This question was a C programming question. Let me know if you have any doubt on this question. So what we are doing here, PT is an struct array of struct which is basically having two elements. So this is how PT looks like in memory, right? It is an array of struct. So if it is an array, so there will be two elements, each of type struct, and each struct is containing three elements. One is 200, another one is 40, another one is a pointer to begin. And where this begin is in the static area, right? A pointer, a character type pointer to begin. Right? Similarly, it will be having three elements. The first element is 300, another element is 100, another element is basically a pointer to end. Right? And these are then the static area, and then this is I mean, if it is a global variable, then this is the static area also. If it is a local variable, then it is in stack. Anyway, PT is an array name, so that's why PT is pointing to the first element of the array because it is an array name. So PT, I can say, is a pointer of type struct. And then PP is also the same thing as PT. So PP is also pointing to the first element. Now they are saying which of the following prints G. So G means they want to access this particular element. If you want to access this, you can either access using PT or you can access using PP. So you can access it using any one of them. Let me show you that how many possibilities are there and how many ways you can access this G. Right? So let me show you. See, if you want to access this G, since these two are pointers, PT, and remember that PT is also an array, right? So what you can do, you can access, since these two are pointers, you can access like this. You can say if it is a pointer, then using an arrow operator you can access, or maybe if it is also a pointer, using arrow operator you can access the first element. I mean the member here. Since it is an pointer to this, so and this name is like field name is name, so it is basically PT name, PP name, using which you will be getting this particular address. Now it is a pointer, it is a character type pointer. PT name is a character type pointer. You want to access the G. So if you do +2 here after the PT name, then you will get to this G, and then you put the star. So that's how you can access this, right? +2. Using both of them, you can access this G. Okay, I hope you understood. Now you can also use the dot operator if you are using I mean if you are using the dereference first time, if you are not using the arrow operator. So basically what you can do, instead of this arrow operator, you can use the dot operator. You can say this is star, and then first you do the star, that's very important, then you do name. So basically this thing is equivalent of saying PP of name. This is just a shortcut that we used because we have the linked list in place. So this is a shortcut. But using the long cut, I mean, this is the actual method. You just put the star first, which means now this PP of star means, I mean, if PP is a pointer type array, if PP is pointing to, if PP is pointing to pointer to or pointing to struct, then star PP is one struct. Star PP is struct basically. Okay. So this is some struct that you have, and then if this is a struct name, then you can use the dot operator. But if you do directly, okay, I mean if you not put star here, if you not put the bracket here, then since the dot is having the higher precedence, it will be problematic to you, right? So you will say pp dot name. It is a pointer, and then pointer, for the pointer dot is not defined, so that's why it will be error. Now let's just see. See, star pp, that is fine, and then this is the struct name, then dot operation is fine, then plus 2, this is fine. Now if you are not putting the brackets, then this pp dot name will be executed first. Since pp is a pointer, for the pointer dot is not defined, so this is a compile time error. And then since it is a pointer, you can definitely do it plus 2, which means you are going to g. Now it is an address of g, and then once you are pointing to this g, then plus then this star means then you are actually getting this g. Okay, cool. Let me know if that question was tough or easy or a good question. I'm moderate, tough, easy. What do you think? Given that this was a C programming question of 1 mark, then what do you think? Okay. Now let's go to this question, which is very nice question, very important question to understand that how the parsing work. See what they are saying. Given below is LR0 automata. This is an LR0 automaton. What could be the contents of the stack have been if it is known that parser is in state 3? Where they are saying that parser it is in state 3, then what could be the content? See, let me just copy this automaton. I think any one of you can draw the automata easily. LR0 automata is not tough to create. So let me just copy this automaton, and then what is the grammar that you have? The grammar that you have is basically this. Right? Now they are saying you are in the state 3. What does this mean of saying you are in the state 3? Let me just do one thing. Let me just take some string, maybe a b, which is in the grammar. Okay, let's suppose this is the string which is in the grammar that I have, and I want to parse this string. Now how to parse using the DFA? Let's just first understand this. Maybe this is the first time that that you might you might be getting that kind of explanation. You might be understanding this. Okay, so you might have not known this, that how to use this parser actually. See here what we are doing. This a will come, so there is a stack, right? So let's suppose this is some stack content, and this is the input that I have. So initially stack is empty, and I can say it is starting with dollar. Okay, maybe, or I think dollar is not necessary. Okay, so input at the end you must be having dollar. Okay, now you are having a. You will say that okay, at a I'm in the initial state initially in 1. If a comes, then I will go to state 2, and I'm shifting, right? This is what parser is saying. Shifting means you're putting that in the stack. So this is basically to start with. Now if a comes, okay, this is the next look ahead. These are basically telling you the next look ahead. So this is this a means this is the next look ahead, right? Next symbol. Now if a comes, you are going to the state 2, from 1 you are going to 2, and then you are shifting, right? It means you have a here. Now you do not have a anymore here. You just have a b, and now your state is 2. So initially, let's suppose this is the state 1. Now your state is, so it is 1 a, and then you have shifted this a. Now you are going to 2. Let me know if that is fine. So basically, how you are using this DFA is basically you are taking the say, you are running the DFA, and then you are going to state 2. Now again a comes, then what you will do? See, now again a comes, you are in which state? You are in the state 2, right? You are in the state 2, and I am writing the state on the top. If we are in the state 2 and the again a comes, then what you will do? You will again shift it, and then you are just having AB here. You are having 1a 2a. Now just listen here. Now you are in state 2. If a comes, you will again go to state 2, right? So that's why I am writing 2 here. So basically state I am writing on the top of the stack. That's the one way. That's the one way of basically I can say that's the one way of running the DFA. But let me tell you one more intuitive way. Okay, this is the actual algorithm, that's how it works. But let me tell you one more intuitive way. If a comes, you will go to state 2. Okay, if a comes, that's fine, you will go to state 2. Then a again comes. Now there are two options. You are in the state 2, and then a again comes, you will be in the state 2, like that, right? So this is the stack content. I'm not maintaining the state. So first a comes, you consumed it, you shifted it, right? Now next a comes. So from here, what you can do, see, this is basically till now you have seen, let's suppose a and a. Now what you can do, you can rerun the DFA. That's very important to understand what do I mean by rerunning the DFA. You can rerun the DFA if you forget like where in which state you are. So let's suppose that after this A you are in state 2 but you forget, okay, which means you can rerun the DFA and then you can say that okay, after this A you are in state 2 and then from this state 2 A comes, then again you are in state 2, right? So what I'm doing here is that I'm writing some string which is AAAB, okay, I'm writing some string which is AAAB. Now, actually this example is not very much suitable to explain the idea which I am going to explain you, but anyway, that's fine. In the marathon, in the compiler marathon, I will tell you that how does this, DFA work. So basically, what I'm doing, I'm basically putting a bar. Bar means that this is what I have seen, okay, this is what I have seen. This is what I'm not seen, okay, not seen. So that's how I'm putting the bar. Now, what I'm saying, let's suppose that initially A comes. So basically you have seen A, you have seen A, right? And now you are in the state 2. Let's suppose I'm not remembering the state. I mean, I will every time I will rerun the DFA. Now, or let me write state here. State, you are in the state 2. That's fine. Now let's suppose in the next you are again getting small a, right? You are again getting a small a. So you will be saying that okay, I have seen A. Now, if someone asks you what is the state, then what you will say? What you will say? You will say that okay, see after this A, after the first A I was in state 2, then after this A, I am basically after this A I was in state 2, right? So here I was in state 2 and then one more A come, I will be in state 2 again, right? So here you will say I will be in state 2. But instead of doing something like this, which means instead of remembering, instead of taking the help of the previous action, so previously I'm just saying that you are in state 2, but instead of taking the help of this, can you rerun the DFA? Just rerun the DFA for small a, okay? Just rerun the DFA for this small a, then you will get to know how. If you rerun the DFA, then you will say, okay, after small a, you are in state 2, that is what I could have remembered, but let's suppose I do not remember, and after the small a, you are again in state 2, right? So that's called rerunning the DFA. As a human you can rerun the DFA, but there's not a point to ask to rerun the DFA for your algorithm. Reason being that you can easily remember the state, right? Okay, now again A comes. So basically if again A is coming, now tell me, if you are having A in the stack, then in which state you are? You will say that okay, previously I was in state 2. From this state 2, if I'm getting A, I will be in state 2. That's the one way of saying that you are in state 2. But instead of that, what you can do, you can say that okay, I have forgotten that previously where I was. Let me just rerun my DFA. Then after this A and then triple A's, you are in state 2. So basically, if someone give you the stack content, can you not tell me the state? Let me know. If someone give you, then finding state is very easy. Is this okay to everyone? Okay. Okay. So the finding state is very easy. So basically, based on the stack content, you can rerun the DFA. That's the only point I want to make. And then you can find the state. But now they are asking a question in the opposite way. They are saying you are in the state 3. You are in the state 3. Then which inputs must have been okay in the stack? Maybe you are starting here. Maybe small a, and small b may have led to state 3. Right, small a, small b, maybe directly small b, only small b, maybe small a and then multiple times loop a and then b, right? So these three contents. Can you tell me if small a capital S comes, then will I be in the state 3? No, right? Either small b or just small b, right? Just a small b or a small a and then any number of times a and then b, right? So something like this. Actually, I will explain this in more detail because that's very important to understand that how does the DFA works in the parsing marathon. Okay, so there I will explain this. But they are just saying you are in the state 3. It means that the stack content could be A, could be AB, could be just B, something like this. Could be A, could be AB, could be sorry, no, not could be A. It could be AB, could be D, right? I mean, with the A, you will be in the state 2. The parser content is this. Okay. I hope you understood this, right? Cool. Let's just move to the next question. Actually, this is very nice concept, to be very honest, like rerunning the DFA and then understanding that how does this DFA works to parse. I mean, how does this DFA is actually helping us to the parse. So that I will cover in the compiler marathon. That's very interesting to how to see this DFA, that it can actually parse, right? I mean, there is a two things. One is that you know how the parsing work, which is like this. I mean, you basically I think I have written it. Okay, you basically maintain the state like one A2 something like this. You maintain the state in the parser. That is okay for a algorithm. It suits good. But as a human, I should be knowing the intuition behind this DFA, right? Which is actually the rerunning the DFA, rerun DFA. That I will tell you in the marathon. Okay. Now let's see this question. So this question is also very easy. What they are saying, that which of the token will never be generated. Now they have given the description. They are saying that we are applying these 4 rules, and we are saying that these rules are in the order of this one. Rule 1 is greater than rule 2, which means you will be applying this rule 1. If this rule 1 matches, then you will say that okay, it is matching. I mean, there is not a problem. That then you will give the answer, right? Now, I mean, if any of the rule matches, you will say that okay, this is the answer. Let's suppose that the string. Let's suppose the string is maybe I say that string is ABC. Okay, ABC. Tell me which rule is matching. Which rule is matching for the ABC? I think only rule 3 matches, right? Only rule 3 is matching. So that's why you will say that token number 3 will generated. I mean, you will assign this ABC to token number 3. ABC means something like int, like int to int I assign, let's suppose t underscore int, right? This is the token. Similarly, for any string ABC, I am assigning the token number 3, right? Okay. Now suppose that AA comes, then what you will do? Which rule is matching? The rule number 1 is matching, right, for A, and no other rules are matching. So you will say that okay, for A you will return the token number 1. But let's suppose that if multiple rules are matching, let's suppose for the strings like C, okay, CAA, let's suppose this is the string. For this, rule 2 and rule 3 both are matching. So that's why I will take the rule which is having the higher priority. So I will take the rule 2. For CAA, I will take the rule 2. In fact, whatever this rule 4 can generate, for that I will never use the rule 4, which means for just for CA, since these two rules are matching, I will take the rule 2. For CA, for CA, since these two rules are matching, I will take the rule 2, because rule 2 is having higher precedence, right? So that's why anything that can be generated by this can also be generated by rule 2. So that's why I will always prefer the rule 2, and I will never generate the token 4. Let me know if that is fine to everyone. So that is the answer. We will be never generating the token 4. Yeah, this question has been done wrong by many of the aspirants, and I don't know the reason, because I have explained this multiple times. I have given this particular set kind of questions multiple times in the mocks also, and in the I think AIMT 1 also we have given the similar kind of question. In the PYQ also they have asked the similar kind of question. So there are multiple variables. One variable is global, one variable is local. Does not matter. Okay, this is the global variable that I have in the static area, which is 0, and there is a local variable that I could have in the stack, which is also 0, right? Local v. Now whenever you do fork, you are going to create an identical copy of this. Everything will be copied, everything. This global v will also be copied, this local v will also be copied. No one is saying that only stack content should be copied or only static content should be copied, right? Everything could be copied, will be copied. So here, now after this copy, you have two local v, right? This local v and this local v are different, which means physically, see, this is the logical view I am telling you, but physically you have this local v here. Here you have also, after this is the child, here also you have this local v. So logically it seems like that both are having the same address, maybe, right? Maybe they are having the same address, because you are copying the logical address identically. But physically this has been stored wherever this page, right? Wherever this page is stored, this has been stored at that particular physical location. So wherever you are storing this page. So basically physically this local v and physically this local v are different. right? I have given this question in the AIMT one also, but from like I was just surprised that why people were not able to do in the AIMT two, because physically these local and global variables whatever you are having, these are different physically. I mean these two variables are different, these two variables are different, because 4 creates the identical copy does not mean that it doesn't copy the global variables or something, right? It creates an identical copy and physically everything is different. If you print the logical address, maybe it is same, and that's where the one of the PYQ has been came. So logically these two could be same. I mean logical address of this and logical address of this has may be same. I have given you the link and please just watch that lecture, because there is no point in again and again explaining the same thing. I have given the link of one of the lecture in the answer. Please go through that lecture and then you will get to understand the form. Let me know if any of you have gone through that lecture. Any one of you? Okay. Cool. So that's why like it will they are saying what numbers will be printed on the execution of above code. So since child equal to 0 means it is a child and it is a parent. So in the parent you are having 1 1, in the child you are having 0 0. So that's why A, very simple question. That's why I put it for 1 mark only. Okay. I hope that question was easy. They are saying that what will be the linked list length, the size of the linked list if the initially linked list is empty, right? So the sizes could be from 0 from 1 to 3, because what you will do, you will be basically running this. So what they are saying is that there are 3 threads which are run the exactly once. So whenever the first thread comes, it will be creating one node. It will say node dot key equal to key and node dot head equal to head, and then there is some head, this is the node, there is some which is n, basically which is n, and there is which basically the n is some node which is pointing here. I mean n equal to malloc size node means n is pointing here, and there is a head which is also, I mean it is currently not pointing, but I want it to point, right? So once I write a head equal to n, it will also point to this. Cool. Now what will happen if some new thread is coming, right? So you will create let me just tell you, and every thread what every thread is doing, every thread is creating one node, one node. These are the 3 threads, there will be 3 nodes, because every thread will be executing this. And then what they are saying, the code is executed by the 3 threads exactly once without adding the synchronizing parameters. What are the possible sizes? Then they are asking about the possible size. Okay. So can you tell me what you should be doing here? See, there are three struct nodes that you have, and then they are saying you can assign the key and the next to be head. Okay. Key equal to key and next equal to head. Yeah. So basically key equal to key, whatever key you are passing, right? And the next equal to head. Head is initially not pointing anywhere, right? I mean, let's suppose it is not pointing anywhere. Then what you will say, that initially it is empty. Then head this n next equal to head. So this is the n next, that will point to, let's suppose it is null. Okay, initially it is pointing to null. This is the n next, that will point to whatever head next is pointing to, which means it will also point to null. And then head will point to whatever n is pointing to, so basically head will point here. Now what they are saying, that if you are running it 3 times again and again, then what are the possible sizes of the linked list? Yeah, that's a nice question. Let me just copy it there. So see, when this thread runs, right, then what it will do, it will create one malloc. It will assign the key, and then it will say that should be pointing to this should be pointing to whatever this head is pointing to. So basically this is saying this should be pointing here, right? And then this head should be pointing to whatever n is pointing to here, which means that maybe I can show you like this. Let's suppose this is the first thread. Okay, instead of like this, let me say, I mean the diagram will look little nicer. So this is the head, and this is the first thread. Okay, this is the first thread. So it is saying that you assign this key, you point to whatever head is pointing to, which means you point this to null, and then head will start pointing here, right? Okay. and then let's suppose the next comes. Okay, I'm not currently interleaving, but let's suppose the next comes. Then in the next thread, what you will do, you will be basically saying that okay, if the next thread is coming, then it will assign the key. It will point to whatever head is pointing to. Since head is pointing to, okay, since head is pointing to this one, head is pointing to this one, so it will also point to this one, right? So they are saying next, and next it will point to this, and then head will start pointing to, head will start pointing to this one. So basically, if you do it sequentially, it will be a linked list of size 3, isn't it? Head will start pointing to this one, right? Now, suppose you do this. Now, what you will be doing? You will be saying that if this thread is running again, then this will point to whatever wherever this next will point to wherever this head is pointing to. So, which means it will point here, and then head will start pointing here. So, this is what the sequentially it will be doing something like this, right? This is how the sequential representation or the sequential execution looks like. But if this is not sequential and head is a shared, right? Head is a shared variable, and then what you will be doing, and n is a local variable, which is a local variable, does not matter. But what you will be doing, if let's suppose these are the 3 threads that you are having, and these 3 threads, let's suppose, are creating something like this, right? Initially these are the something like this, that these 3 threads are creating, and it is null. It is null. Then you want your head to point to, I mean, this will say that this head will point to whatever this n is pointing to. Basically, locally there are 3 n's. This is pointing here, and there is one n which is pointing here, there is another n which is pointing here, isn't it? Okay, so now let's just see that they are saying that n key you can there is a no problem in this, that n key you can definitely assign, n key you can definitely assign, n key you can, because this is the local operation that you are doing. Now n next should point to whatever head is pointing to. So suppose that initially head is null, suppose that all of them execute this. So for all of them, everyone will pointing to null, isn't it? If all of them execute this, then for all of them, everyone will be pointing to null. Then the next line will say that head will pointing to whatever n is pointing to. Then everyone execute this. Then everyone execute this. Then head will be pointing first here. Then it will be pointing here. It will be pointing here. So basically, there is a linked list of size just 1. Right? Let me know if you have understood this. Yeah, thread will share the local data. Locally, the global data they will share, but locally whatever they want to do, they will be doing in their own premises. Let me know if that is clear. I mean, at least this is clear. Now we need to see that okay, one length is possible, 3 length is definitely possible. Is 2 length possible here? That's what we need to see, right? 2 lengths possible here or not? Let me know. See, you can also check that two length is possible. How? You will say that okay, what you can do, see, n is pointing here, this thing is fine, like n is pointing here, and then n key is also fine. So basically, these two statements are local. These two statements are local, so that's not a problem to anyone. So n is fine, n key is fine, right? Okay, sorry. So let's suppose that n and n key, these two operations are local, so you do not have any problem. So now you will come here, you will just check that this you are assigning to whatever head is pointing to, right? So suppose you do this, and then head is null initially, so now you will do what? It will be pointing to null. I mean, one of the thread will be executing, and then it will be pointing to null, isn't it? So any one of the thread you can take. I'm taking this one, it will be pointing to null. Now a head will start pointing here, and let's suppose this get completed, head will start pointing here. So that's where the difference will be. See, earlier what I was saying, that earlier this is pointing to null, and then this get interleaved. You are not modifying this head. Okay, let's suppose you are not modifying this head. This head doesn't get any node. And then if that get interleaved, so everyone will be pointing to null, everyone will be pointing to null, and it will be a problem to us. Now if everyone execute this, then it will be just a linked list of head of the length one, right? But now let's suppose that that head start pointing to this. I mean, one of the thread actually execute this head equal to n. Okay. So what's going to happen? See, earlier if everyone is null, then this head is not getting any node, and if head equal to n you execute, it will be getting just one node. But let's suppose I make a linked list of two first. I make a linked list of two, which means I ask this to point here nicely, and then what will say that okay, this is pointing here. Then the next thread comes, it will say that okay, uh, yeah. So this key is done. Now this next equal to head. It will say that okay, let me point to whatever head is pointing to, and then let's just say that head is pointing here now, right? Okay. After these two threads, it will be the story. And now this third thread can maybe it has already executed it to null, right? It has already executed it to null. So the key idea here is that you are having, let me just again explain the complete idea. You are having the three nodes here, which you can definitely create, right? I mean, there is a like creating a node and assigning the key is not a problem to anyone. So let's suppose you definitely create, definitely assign. Okay. Now the critical point will start from here, that you are trying to access the global variable. Okay. So let me know till this point, is this clear? And now I will explain again that how it is behaving for this particular these three lines. Okay. So now there are a couple of options. One option is that, see, this head is currently pointing to null. Okay. There are a couple of options. One option is that you say that everyone next is pointing to null now, right? Everyone is actually executing this. So pointing to null means now it is the end of linked list. See, you are executing this just once, right? Now you cannot extend your linked list. Once you point to null, then it is the end of linked list. So which means one option is that, see, you executed till this point, everything is fine. Now this is the first option. First option is that you say that, see, now what I'm doing, I'm saying that everyone is pointing to null, everyone is terminated, everyone is terminated, everyone is terminated. Now there is not much benefit because head equal to n. Now head will be start pointing to, head will just get one of the node. It will start pointing here. Then this thread will say head is pointing to me. This thread will say head is pointing, right? So that's what is going to happen here. This is the first option that you can do. As in second option, what you will do, you did this local operations. Now you will say that okay, this next is actually head, like let's suppose one of the thread is executing this, because anyway one of the thread will be executing this. So which means that for one of the thread it is null. Now let's just one of the thread at least do the completion, which means let's just one of the thread execute this, and this is the next line, which means this head get one node, at least one node, right? If it is getting one node, then it is good. So basically, first thread execute the null and then execute this. Now these are the two threads which are at here, right? Because they have done their local operations. Okay. Let me know if that is clear. Now what you can do, you can say that, see, this can point to, now this can point to the whatever, wherever the head is pointing to, and then just see here. Now this can point to, this is the second option that I have. This can definitely point to wherever the head is pointing. And then let's suppose you do not modify the head. Okay, that's important. You do not modify the head, and this is also saying that let me just point to wherever the head is pointing to. So for these two remaining threads, you are executing this line back to back, this particular line back to back, right? And then you are saying that head equal to n. So any one of the thread whichever is getting scheduled, for that you will be just assigning this head, right? Now you are saying head equal to n. And then you will say that, okay, head is pointing here, this is pointing here, but no one is pointing here, right? This is also the case. Or maybe if it is getting null or something, I mean, doesn't matter. Basically, there is a possibility that you can get a linked list of size 2. So that's very nice question. You have to do it very carefully. That question, I think I have taken that question from Stanford or some top university. Let me just check from where I have taken this question. This is from Stanford or some top university, I'm sure. Question number 17. A second, I will tell you. Okay, not from Stanford, but yeah, from the Stanford University, I have taken this question. So this question has been taken from this university. Let me just paste it. That question is very nice. If you have done it correctly, then it is really good, right? That question was very nice. I've taken this question from this university, from page number 19. Okay. Anyway, let me know if you were able to do it correctly in the examination. Cool. Let's just move further. Let's see this. Okay, I hope that question is also done. We have done this in the marathon. I have given the link, and there is a major misconception in this question, which is basically people are dividing this receiver window by 2, right? Actually, for the threshold, you have to divide the congestion window by 2, not the receiver window. But people were dividing the receiver window. Let me know if you people have done the same mistake or you were able to do this question. Okay, okay. So you divided by 2. In the marathon also, I have given this very clearly that for the receiver window you cannot divide by 2. I have given the standard reference. I have also told that this is a common misconception that people have, right? And that's why I have given this question in the mock, in the AIMT, so that I just want to let you know that you should not be doing in the gate if that kind of question comes in the gate. Okay. That was very easy question. It was a probability question. They are saying that what is the probability that after x equal to 2, you will be again at position 0. So basically there are a couple of options. For 2 seconds you stay here only, which means that you say that for 2 seconds you are here. I mean, you are x equal to 0 only. There are a couple of ways. Another way you can be at here. You may first go left, then you go right, or maybe you first go right, then you go left. There are three things that can lead you to the same situation. So basically, the first probability is p3 square plus p1 p2 plus p2 p1, which is this one, right? So that's why this is the correct answer. Okay. Now let's just move to this question. This question was little tricky in the sense that I have said like x and b both are in r power n, right? X is in r power n, b is also in r power n. Generally, x is in r power, see, if this is m into n, then x is n cross 1, and finally you get a b which is m cross 1. Generally, b is in m, right? B is in m. But if I am saying b is in r power n, it means m must be equal to n. Okay, it is not given in the question, but it should be inferred from the question. It is saying m equal to n. It means that it means if you are having rank n, and which is basically n cross n matrix, rank is n, which means every row and every column is having a pivot element, and it means that it is a full rank matrix, right? Full rank matrix means there is a unique solution. So that I have covered in the marathon also, like how to find unique solution and all. Let me know if you have watched the linear algebra lectures. Have you watched those linear algebra lectures that I put in the marathon? So that question I have taken from there. I mean, I formulated this question with the examples of that I have given in the marathon. Okay. This question was also easy. They are saying that you are at the position 0, 0, and then you want to move to this position. So what you can do, there are, let's suppose these are the different dots, okay, different dots of the grid. This is the grid that you have, and then you want to move to, from this position, you want to move to this position. So basically, you will go here and then you will check what are the possible number of ways. Then you will go here. I mean, there are two ways. From here you can either go here, either go here. So total wage from here, total, let's suppose total wage from here is x, and let's suppose total wage from here is y. From here is y. Then what is your answer? Your answer is just x plus y, isn't it? Or you should be adding one. You should be adding one. Let me know. Should you be adding one here, or just x plus y? You want to know what are the total number of wage from here. So it is basically the total number of wage from here and total number of wage from here, right? And then you will be getting the total number of wage from here. So you just need to do plus x plus y. Let me know, you should you be doing x plus y plus 1? Yes, I will be solving that Hoffman code question. Don't worry. Okay. So that is why the answer is here A, not the D. One of the student, I got one of the comment in the GATEOverflow that he was confused between A and D. See, D is saying 1 plus, but why you need to do 1 plus? Right? So there is no point in doing 1 plus. So that is why answer is A. That was 1 mark question because that was an easy question to me. Let me know if you think that was an easy question or the tough question. Okay, let's do this question, which was a Hoffman encoding question. It was also very nice question. What they are saying, okay, the solution I have given there, but let's just solve it here also. So they are saying that these are this is the Hoffman tree that you have got, and these are some comments that I have. So they are saying the first comment, the frequency of A is strictly less than the frequency of B. Okay, so maybe it is true for some message. It is true for some message. It depends on the message. May not be false, may not be true for all, may not be false for all. It depends on the message. So definitely P depends on the message. That's why it is C. Right? It depends on the message. Let me know if P maps to C is okay to everyone. Okay. Now let's just go to Q. What this Q is saying, that the frequency of C is greater than or equal to frequency of A. Frequency of C is greater than or equal to frequency of A. What do you think? Can greater than or equal to. So basically frequency of C, it is as good as A. First of all, it cannot be less than A, because if this is less than A, let's suppose, see, this is already in the top hierarchy, so it cannot be less than A. So let's suppose this is coming 3 times, and this must be coming at least 3 times. This B itself must be coming. I mean, okay, this can come greater than 3 also. Oh, sorry. Yeah, this can come any number of times. But let's suppose that if I'm having this C here, okay, if I'm having the C here, it must mean that it must be greater than A. If it is less than A, let's suppose, let's consider a scenario. Okay, just, or maybe I can go to the next page. Okay, so let's suppose that I have this situation. Now I want to claim, my claim is that C must be having, C frequency must be greater than or equal to A frequency. Suppose that that's not the case, C is having the lesser frequency. Then let's suppose it is A is having some frequency, maybe let's take it anything, maybe 3. Okay, maybe 3. And let's suppose B is also having some frequency, maybe you can take it to anything, maybe 10. See, in the Hoffman coding, what I do, I take the smallest frequency first. Now these two are smallest. Now C must be, right? See, it must be 310. Now this number should be C. I always take the smallest. This is the two smallest. If these are the two smallest, then C automatically makes the C to be greater than or equal to A and greater than or equal to B, right? It could be anything. I mean, it could be anything which is greater than or equal to 10. Because I always take in the increasing order, right? In the increasing order, it could be anything which is greater than or equal to 10, maybe 10 also, maybe 11. So basically in the Hoffman coding, I always take in the increasing order. Is this clear to everyone? Let me know if there is any confusion here. See, in the Hoffman coding, I always take in the increasing order. That is why C must be greater than or equal to 10. Okay, must be greater than equal to A, must be greater than equal to B. Let me ask you another question. Let's suppose that frequency of B, okay, suppose B frequency is greater than A frequency, suppose, then tell me what about relationship between C and A frequency? What about relationship between C and A frequency? See, it is always in the decreasing order. So if it is A frequency, then it must be B frequency, then it must be C frequency, right? If it is greater, if it is strictly greater, C is always like I'm writing in this order. See, from this tree, once that is one thing which is very much clear. You can say that from this tree, A frequency, you must be writing something like this: A frequency, B frequency, or maybe B frequency, A frequency. You don't know, so that's why I'm writing in the box, right? I mean, you can flip them, right? You don't know the particular order, so you can flip them. But it is the case that then the C frequency will come, right? I mean, you can flip them. That's not a problem. But then the C frequency will come. If B is greater than the A frequency, then C must be greater than this B frequency and A frequency also, right? So C frequency is actually greater than or equal to B frequency, and it is also greater than or equal to A frequency. But since C is already greater than or equal to B, then and B is greater than A, then C must be greater than A. Okay, maybe I can just first explain the question that is there. So this Q is saying the frequency of C is greater than or equal to the frequency of A. So is this okay? The C that is actually true for all the messages. The C frequency cannot be lesser than A, because these are the two smallest, right? Since these are the two smallest, so that is why C cannot be lesser. It may be equal. I'm not saying it is not equal, but these are the two smallest ones. So C must be greater than or equal to A, must be greater than or equal to B also. So that's why this Q is true for all the message. The frequency of D is strictly greater than the frequency of A. Frequency of D is strictly greater than the frequency of A. Yeah, that is interesting. What do you think? See, this I know that AB is smallest, and then C will come, right? And then D will come. Now, can this be equal to A? That is very interesting. I mean, observation. See, A frequency will come, B frequency will come, C frequency will come, and then D frequency will come. This is the order, increasing order, right? I mean, not strictly increasing, but yeah, I know that maybe these are equal and all. Let me know that if these two frequency could be equal. See, if these two frequencies are equal, then it must be the case that all of them must be equal. See, it is basically something like this, right? I mean, you can flip these two. I'm not saying that you cannot flip, but yeah, it is either this, or maybe let me go to this page here. So let's see that what is the order in which I have the frequencies. So you either have A and then B, and then maybe C and then D, right? Maybe this, or maybe you can flip these two, right? Which means you either have this, and then this is basically the relationship is less than this less than equal to, which means that A is less than equal to B, which is less than equal to C, or something like this. So since it is less than equal to less than equal to less than equal to, then if I'm saying this and this are equal, okay, suppose this and this are equal for a counter example, then it could be the case, but in this case it cannot happen. I mean, it could be the case in general. If this and this are equal, then all of them in between must be equal. A, B, C, D must be equal, right? If all of them are equal, then this C and D must be equal. Since C and D are equal, so that is why it will be a binary tree. I mean, it will be like this. It will be a perfect binary tree. You will be having something like this. You will be merging A and B, and then you will be merging C and D. If we are not merging this D, it must mean that it is basically not equal to A. I mean, uh, it may be equal to C, right? But the combinedly, it is this frequency combinedly, whatever A and B are getting, this is the combined frequency. This frequency and this D frequency could be same. This could be same. This frequency and this C frequency could be same. But if A and D are same, then C and D must also be same. See, let me see the explanation. Let's see what they are saying. They are saying clearly D frequency is greater than or equal to frequency of A. Suppose they are equal, then since Yeah, the same thing they are saying. Since frequency of D is greater than or equal to frequency of C, which is greater than or equal to frequency of A, then we must have frequency of D, C, all of them should be equal, then it will be a binary tree, right? See, that's the relationship. These are the two smallest one. Then you have C, then you have D. I mean, this is in general it is greater than equal to, right? In general it is greater than equal to. Now I'm saying it is strictly greater than. It cannot be equal to, because if it is equal, right? In general that's the case. So that's the general rank. I mean, that's what you can definitely infer. This is not incorrect. This is correct only. But I'm just being more precise. Okay. So this is correct. This line is correct. By looking at this tree, you can say this line is correct, right? Let me know if you are understanding, you are with me or not. By looking at this tree, you can say this line is correct. Now I'm just being more precise. I am saying that these two cannot be equal. If these two are equal, then these three must be equal. And then in this case, it will be a binary tree. It means you must be, if C and D are equal, then you must be merging C and D. Right? But that is not the case. See, if all of them are equal, if all are see, if these two are equal, then if all of them, if D and A are equal, then all of them must be equal. A, B, C, D, all of them must be equal. Then it will be like this. If all of them are equal, then it will be like this. But it is not the case. So that is why this is false, right? I mean, this D is okay. Strictly greater than, yes, strictly greater than is true. So it is true for all the messages. So R is A. Strictly greater than is actually true. Cool. Let's see the last option, which is saying that the frequency of D is greater than or equal to ABC combined. It is greater than or equal to ABC combined. What do you think? So ABC combined, can the frequency of D less than ABC combined? Definitely, right? I mean, this frequency is ABC combined. This frequency is ABC combined. Can this frequency be less than also to D? It could be the case, depend on the message. Very easy, right? It depends on the message. I mean, this number could be anything which is less than, strictly less than D. So D could be, okay, they are saying D is greater than or equal to. So they are saying D is greater than or equal to. Maybe, or maybe D is less than. I mean, this particular frequency is let's suppose too high, right? Maybe let's suppose this is 3 and this is 4, then this will be 7 and this is 5, this is 12, right? So basically this is 3, 4, 5. No problem, right? I will be merging this, then I will be getting 7, 5. Okay. Now, let me know what is the frequency of D. Frequency of D could be, can it be 6 less than this? Definitely 6, right? If it is 6, not a problem. I mean, this is 6 12, not an issue, because this 3, 4 I have taken. Then okay, okay, this cannot be 6. That has to be greater than 7. Let me take something, maybe 8, right? That has to be greater than 7, basically, right? It should be greater than 7. If it is not greater than 7, if it is even less than 7, then I must be combining C and D. So it has to be greater than 7, maybe 8, or anything greater than 7. It can be anything. Anything greater than 7. Can it be equal 7? Let's just think. See, this is 5, right? Yeah, this can be equal to 7 also, right? Yeah, greater than equal to 7. Can it be less than 7? Can it be 6? No, it cannot be 6. If it is 6, then I must be merging C and D. If it is 6, right? So it must be greater than equal to A and B frequency combined. See, here this is C, and then if I'm not choosing D, it must mean then it is either this greater than this or maybe equal to this. I'm not choosing it, that is fine, but it must be greater than equal to this, right? This thing, if I'm choosing it later, then it must mean that it is greater than equal to this. Similarly, if I'm choosing this C later, then this A, it must mean that C is greater than equal to A, C is greater than equal to B. If I'm choosing something later, then it means it is greater than equal to relationship, right? They are saying D is greater than or equal to ABC combined. No, ABC not combined. It is greater than or equal to AB combined. AB combined, right? For ABC combined, this I'm actually, these are two on the same level. For the same level, I cannot say it is greater than or equal to, right? These order could be flipped. I mean, I do not know the relationship at the same level, but I know the relationship at the different levels. I know the relationship between A and I know the relationship between C. I can say that C is greater than or equal to A. I can say C is greater than or equal to B. I can say D is greater than or equal to AB combined at the different level they are. I cannot compare D and this, right? I cannot compare A and B. But I can definitely say that C is greater than or equal to A, right? Let me know if that is clear. Okay. So let me go through this again. The frequency of A is strictly greater than the frequency of B. Is this true? Maybe it depends on the message because they are on the same level. If you are comparing on the same level, I don't know actually. I mean, it depends on the message. If comparing on the same level, depends on the message. The frequency of C is greater than or equal to the frequency of A. Yes. Comparing on the different level, then it is always true, right? Then it is Q is always true. Comparing on the different level, then frequency of A and frequency of C you are comparing, then it is always true, right? On the different level, I can definitely comment it out. Frequency of D is strictly greater than the frequency of A. Yeah, that's interesting. The frequency of D and frequency of A. That's very interesting. They are comparing two levels and one is skipped basically. One is skipped, not the immediate level. Okay, if one is skipped, then it become more interesting, and then all of them. I mean, if A and D are same, then it means C is coming, right? See, if one is skipped, then you know one thing, which is basically this. You know that D is greater than or equal to C because they are on the immediate next level, and then C is greater than or equal to A, right? And then if you compare D and A, then you will say D is greater than or equal to C greater than or equal to A, which means D. If they are saying D and A, they are saying strictly greater than or equal to. Let's suppose they are not. It is greater than. It should be greater than or equal to A. But let's suppose if it is equal. Okay, if it is either greater or equal. See, this I have written because of the these two levels, right? Immediate levels, right? This I have written because of the immediate level. Now I am combining this. Now I am saying if D and A are equal, then it must mean D and C and A all are equal. It must mean I must have combined C and D, right? I must have combined C and D because these two are equal. So why I have to combine C and D? See, I hope you are getting. See what I'm saying here, the same thing. The D is greater than or equal to frequency of A. Suppose they are equal. Like I mean that's what we know from the different level, right? Suppose they are equal, then this must mean that D, C, and everything has to be equal. If everything is equal, in this C would have been merged to D instead of AB. Why? Because if everything is 2, 2, 2, 2, everything is equal, then you will be merging them, and at the same time you will be merging CD, right? I mean, you will not go to the different level. Since everything is 2, 2, 2, 2, you will be merging like this, right? So that was very, I mean, very, very nice question. I can say it was as per the gate question. So I really like this question. Let me know what is your feedback about this question. So for me, this question was very interesting. What do you think? Okay, let's go to the next question. Yeah, this question was also very, very nice, right? I mean, they are saying that you are having some A's and V's or zeros and ones, and then you want to do the merge sort. Okay, sorry. So basically you are having this and then you want to do merge sort. Okay, let me just copy this. Cool. So suppose you are having this, then what you will do, you will divide that into two half, right? You will divide that two into two half. So you will say that this is let's suppose for example I'm taking 16 characters or the 16 symbols. So you will divide into 8. So this is 1 2 3 4 5 6 7 8. 1 2 3 4 5 6 7 8. So you will be dividing like this, right? So from this one you will say that okay, I have divided into two parts. One will be this, another one will be this, right? These are the two parts that you have. Now what you will do, let me just tell you that what you are going to do here. So basically this is your two halves look like once you divide. So from here you have divided into two parts, right? Okay. These are the two parts that you have. Now let's just see that what we are going to do from here. You will say that, okay, this is the first part, this is the second part. I will sort this separately. I will sort this separately, right? This is what you are going to do. If these are the n elements, then these are the n by 2 elements, these are the n by 2 elements. Now you will sort them separately, you will sort this separately, and then finally you will be just combining to get this, right? So let's suppose that number of comparisons to sort this alone, number of comparisons I'm talking about. Let's suppose if this number of comparisons is Tn to sort this, then what will the number of comparisons here? It will be Tn by 2. Number of the comparisons, it will be Tn by 2. So I can say that after Tn by 2 comparisons, okay, after Tn by 2 comparisons, it will be sorted. Okay, so after Tn by 2 comparisons, it will be left will be sorted, right will be sorted, and then my array will look like this. So this is how we will see it after Tn by 2 in each half. So you will say this is sorted. This is sorted means you will be sorting in Tn by 2 comparisons. This will be 0 0 0 0 1 1 1 1, and then this will be 0 0 0 0 1 1 1 1, right? So after Tn by 2 comparisons, you will be doing something like this. Maybe I can make it more clear. So you will be having 1 2 3 4 1 2 3 4 1 2 3 4 1 2 3 4. Now you need to merge them. So till now you have taken Tn by 2 here, Tn by 2 here, and you sorted them. Okay. So basically for recurrence, always think at only one level. Do not mess up your mind by thinking at the below level. Just think at the top level. Assume that you have sorted it in Tn by 2, right? If this is going to take n, then Tn, then this will go to this will take Tn by 2 comparisons. This will take Tn by 2 comparisons. Now after Tn by 2 comparisons, you will be having this, you will be having this, and then you need to merge. Now tell me in the merging, how much comparisons you will be having? Number of comparisons here to merge them. Let's just check, right? To merge, you will be having one array of length n, because these are n by 2, n by 2. So you will be comparing this and this. So you will be comparing this 0, this 0. You will be writing one of them. You will be 0, 0. You will be writing one of them. So these are the 4 zeros, right? You will be writing 4 of them. Now you will be comparing this one with this 0. Since this 0 is smaller, you will be writing this 0 and then 0, 0, 0, 0. Basically, you will be writing these 4 0, right? And this is done. Now you will be comparing this one with this one. You will be taking one of them. Let's suppose this. Then you will be writing this one, this one, this one, and this one. So basically, you will be comparing and then you will be writing all of those ones. Now this one is also finished. Now one of them has already finished. Now here you have 4 ones. You will you will be writing them directly without the comparing. So basically here you have n by 2 elements, and out of n by 2 you have n by 4 zeros, n by 4 ones. Similarly here also you have the n by 4 zeros and n by 4 ones. You will be writing your n by 4 zeros, I mean you will be writing each of them by comparing, but for the last n by 4 ones, you do not need any comparison. That's the very important point. For the last n by 4, you do not need any comparison. Yes, Devanjan. The same question we have discussed in the probability course. That's true, right? So that is why, yeah, this is from Princeton University. You are right. This one, in fact, this Hoffman code question was also from the Princeton University. So I have taken these two questions from the different assignments of the Princeton University only. So this is also from the Princeton University, and this is also from the Princeton University. So we always take from the standard resources, because that's the way you will be learning more, right? Okay. So you will be having a recurrence. Tn should be 2Tn by 2 to sort number of comparisons, to sort it, number of comparisons to sort it, and then to merge you will be having, and I mean you will be having 3n by 4 comparisons. You will not be having this comparison which is n by 4. Okay, cool. Okay, for this question we have given the counter example. That was an easy question. I mean that's where you have to apply your aptitude. There is no such formula that how to approach this question, but yeah, you have to come up with the counter example in the exam itself. GATE also asks these kind of questions where you have to apply your aptitude rather than the subject knowledge, right? But that is okay. I mean that is fair enough. If you have done proper practice, you might get to know that how to solve these kind of questions. I mean there is no particular thing that I can tell you for this question, but I can just say that from the exam you have to just think through the question. That's the only thing I can say. right? I've just confused you using like given these four options, like if it is a tree, if it is distinct bit, does not matter, right? Tree and these things doesn't matter. This will not even work for this simple G1 G2. This simple G1 G2, if you do this, then this is MST. These are the MST edges, right? This is MST, which is connecting A, B, C, D. You are not even taking any edge from this, any edge from this. So this is just a counter example that we need to think in this particular case. Okay, this is very interesting question. Let's just see what this question is saying. This question is saying a data structure is comprised of nodes of which has exactly two pointers of other nodes. So basically, this is how your struct look like. You are having PQ info and mark. Sorry, PQ info and mark. So basically, this is how your struct look like. You have P is a pointer. There are two integers, info, mark, and Q is a pointer, right? So these are the two pointers that you have, and info and mark, these are the two integers that you have. Now what they are saying that you want to access all the nodes that are pointing from A, right? Which means that this is what you have, this is how your struct look like, and then you want to point all the nodes. So basically there is one A which is pointing to some of this same struct. Now let me tell you how does the data structures look like. How does this data structure look like? So basically these are the four fields you have here. Now it may be a doubly linked list, may not be a doubly linked list, does not matter. Like that's why I have said in the question also. Basically it may point to anywhere, like it may point to here, and let's suppose this is pointing to here, and then this is pointing to here, and these Q's are pointing anywhere, like maybe pointing to null. I mean, then there is no fixed structure. You don't know what is the structure of this particular data structure that you are dealing with. It may not be doubly linked list, could be anything, maybe circular, maybe any mess up, right? Maybe anything, maybe something like this. These are the four nodes, right? These are the, let's suppose 4-5 nodes in the data sheet that you have. Maybe they are pointing to each other. They are pointing to each other, and maybe yeah. So this is pointing here, this is pointing here, and this one is pointing here. Let's suppose this is pointing here, or maybe this is pointing to here. I mean, there could be anything, and any mess up could be there. You don't know what is the data structure. They have said that as our data structure is comprised of some nodes that which has exactly two pointers and other nodes, right? They're not saying it is a linked list or something. That's why I have especially mentioned that it is useful to note that data structure does not have to be doubly linked list. Okay, so this is not necessarily that it will be a doubly linked list. Cool. Now what they are saying, you want to count. So what you will be doing, okay, but yeah, one thing is for sure, they are saying that there is no null pointer, right? So initially 0 all the nodes. So they have said that with no null pointers, which means everyone is pointing to something. There is no null pointer. So why I have said it? Because in the code I have not written the null check. If there is a null check, if I can do the null check, then that is fine. Just to avoid writing the code, I am saying there is no null pointer, so that later you don't blame me that okay, see, there could be a null pointer, your code might not work at all, right? Then all the options are wrong. So you will say that give me marks to all. So to avoid that kind of reasoning, we are saying that there is no null pointer, and we are not adding any null check, right? I mean, if there is a null pointer possibility, then I have to do if a equal null, then return 0, like that. I mean, something that I have to do just to avoid that possibility. I'm saying there is no null pointer, right? Okay. Now they are saying that this is the code. This is the code that you are using to access this data structure. So A is pointing to some node in this data structure. You don't know that how does this data structure look like. Maybe any complex, right? A is pointing to one of the node. Now you want to count all the nodes that A is pointing to. So what you will do, if you will check first, if A mark is 1, which means it is already, so there are two fields, info and mark. So you are saying if it is already marked, then I will say that okay, let me not count it, right? If you are saying that it is already marked, you will say that okay, then you directly return 0, which means I will not count it, right? Initially all mark are 0. So initially all mark are 0. You will say if it is already marked, then it means that, see, whenever the idea is that whenever I am going to any node first time, I will mark it. Okay. If it is already marked, I will not count it twice. So that's why I'm saying that my count for this particular node is 0. Why I'm saying my count for particular node is 0? Maybe because whenever I'm going to the first time to the node, I want to count it and I will make the mark 1, right? If it is 0, which means it is not marked. Then I will go here. I will say that okay, 1. See here, 1 plus. 1 plus means it is not marked. It is 0. It was the 0. I will count it now, and then I will mark it. So basically, I need to mark it. After this, if I need to write a mark equal to 1. Why? Because if it is not marked, if a mark is 0, then I will say that okay, now I'm marking it. Now I'm marking it. Okay. So the code will look like this. If it is not marked, then I will mark it. And then I will say that okay, let me go to left of this. Let me go to count all the nodes which are accessible from left, all the nodes which are accessible from right, and one of this node. So that's how I'm counting. I'm saying that okay, if it is marked, then I'm done with this node. Initially nothing is marked. If it is not marked, I will go here. If it is not marked, I will say okay, let me mark it. Let me mark it quickly. I will say a mark equal to 1, and then I will go to all the nodes that are accessible from left, all the nodes that are accessible from right, and the node itself, right? So that's how I will be doing this question. So that was a beautiful question. Let me know that if you were able to solve that question in the exam. That was one of the most beautiful questions that I have put. So now when I'm solving the question, now I can really realize that all the questions were very good, right? So all of these questions were actually quite good. Huffman code question, and this question was also very nice, I think. And this merge sort was also quite good question. All of the questions are meeting the GATE standard, according to me. Yeah, this question was little tricky. This was sweet question. I mean, you could have done it. This question is actually I want to attack one of the misconception. That's why I put it, right? I mean, so that a student do not do that misconception in GATE. This question was also very nice question, sweet question, right? I've taken this from Standard University. Yeah, that was also sweet question. So I think for me, like this was also nice question. For me, every question is quite nice. Now I can really realize it. I mean, now when I'm solving this these questions, then I'm really realizing that yeah, questions were nice. Okay. So I hope you understood this question. Let me know if you have understood. So what they're saying, a mark you add within the first statement. If you add the as a first statement here, if you add a mark, if you go here and directly mark it, okay, then you will return 0, and then your answer will be 0. So obviously this is false. You add it after if a statement. Yes, that makes sense. As I told you, they are saying a mark equal to 1 at the last statement. If you are adding at the last statement in the node count function, then what will happen? You will go here, then you will say that okay, it is not marked. Let me just tell you what's going to happen if it is a last statement. So if you just add it as a last statement, then what will happen? Suppose you write a mark equal to 1 here, right, as a last statement. You will go here, you will say that okay, initially every mark is 0, so that's why it will not be executed. This if will not be executed. You will go to the left, you will go to the right, right? For the left also you will do the same thing, and then you are marking once something written. Then for the left also you will say that okay, let me go to the left, let me go to the right. Since every mark is 0, then you will be looping around. So it will be infinite loop if you write a mark equal to 1 here. Why? Because everyone, you are not marking any of the node. You are just saying okay, 0 0 0, everything is 0, and you are not marking. So you will keep on looping. You will keep on looping, right? So that's why this statement, this particular option is false. Mark equal to 0 after the statement. So if you put here, the fourth statement is saying if you put instead of mark equal to 1, if you put mark equal to 0 here, then what's going to happen? Then you will say that okay, if mark is 0 here, then a mark initially it is 0. Okay, I don't think it is doing anything, right? If a mark is 0, anyway it is 0, then again it will be an infinite loop, right? Because you are not marking it, so you will never return. Your base case will never get executed. If your base case is not getting executed, then it is infinite loop. Okay. So dangerous Khiladi was saying that sir, all the questions good and quality. So how to approach those kind of questions, because it take too much time to decode the question. Yeah, actually there is again there is no rule or something. Whenever you are getting the intuition that you can solve this question, then just solve it. Otherwise, move to the next question. Gate will not be asking. Similarly, like in AIMT also we have not asked all the questions tricky questions, right? I mean all the questions are not tricky. Some of the questions are very tricky. If you find that you are not able to solve in the one go, just leave it for now. Have trust that even there are too much of mark for review questions, then also it is okay, because it is also true for other students. Don't worry. Okay, that was very nice question. They are saying what is the minimum number of nodes that you must be visiting if ABL tree is height 4. So if you want to find the maximum for the height 4. So basically, if you want to find the maximum, it will be on the right side, right? It will be on the right side. So here you want to keep the minimum number of nodes because you want to visit the minimum number of nodes. And here the maximum, if you can shift, then maximum you should be shifting here. And here you will be keeping the minimum nodes. Here you could be keeping the maximum nodes. Okay. So if the height is 4, then what should be the height of this? See, if you're keeping the minimum nodes, then let me just tell you in general, if you are having two subtrees here, okay, if this height is h, then what are the options for these heights? What are the options for these heights? These both height could be h minus 1 for the ABL tree. Then only it will be the total height will be h, right? Is this okay to everyone? What other option you have? This could be h minus 1, this could be h minus 2. I'm sorry, yeah, this could be h minus 1, this could be h minus 2. Can both be h minus 2? Can both be h minus 2? No, right? Because if both are h minus 2 height, then ultimately height will be just h. So that's why both cannot be h minus 2. One of them could be h minus 1 and another one could be h minus 2, right? If you have the liberty, that's what I'm saying. So here you want the minimum nodes, which means you also want the minimum height. So if the total height is 4, I will keep this height as 3. I will keep this height as 2 only. Just 2 height. Okay. So basically 2 height means that ABL, this is height 1, sorry, height 2, that ABL tree might look like this for the 2 height. Isn't it? ABL tree will look like this for the 2 height. Okay, sorry, this is not balanced. I think it will look like this. Yeah, this is the balance, right? So ABL tree for the 2 height will look like this. Now, if it is, if you want to have here the minimum height, as I said, it will look like this, right? So you can have it, which means here you just have with the minimum height, so that so your 2 height will look like this, and here you want to have the 4 height, right? So can you have the 4 height here? So what they are saying, the question is that the minimum number of nodes in order to visit the largest value of the height 4. Yeah, so sorry, here you want to have the 3 height. So this height I want ultimately to be 4. So that's why here for this I can easily have the 3 height, right? Okay, definitely. So on the right hand side I will be keeping the minimum number of nodes. So that's how I can keep the minimum number of nodes. And if you execute it, if you want to find out the maximum number here, this is 1, 2, 3 nodes. You need to just traverse the 3 nodes, right? Okay, cool. I hope, yeah, that question was also quite nice. See here, sorry, here you are visiting 1, 2, 3, 4, but why you will be doing it? I mean, if you have the choice, then put this on the left hand side only. I mean, you do not need to put on the right hand side. So you put it on the left hand side, because always you want to do it recursively. Always on the right hand side, you want to put the minimum number of nodes whenever the chance is given. So only 3 nodes you will be visiting. Yeah, you should be considering the best case, where the right side of the root has a minimum height, still has a no, right side of the root that has the minimum height such that the total height remains to be 4. So can you adjust the height on the left side? So which means here you have the 2 height and here you have the 3 height, so that the ultimately your height is 4. Okay, cool. So that was also quite a good question. There we are saying that DFS, BFS you are using, and then if it is a tree, then obviously since it is just one tree, then DFS, BFS will be leading to the same output, because there's a tree and the same tree it will give, either you apply DFS or BFS. But if it is not a tree, then DFS, BFS will definitely give you the different answer, which means let's suppose it is having a cycle. Okay, any number of nodes could be there, it is having a cycle. So let's suppose that it is having a cycle, it is not a tree. Okay, if not tree, then DFS, if not tree, then DFS, BFS gives different answer always. Why? If it is not a tree, there will be a cycle, right? Let's suppose that this is the cycle that you are having. Okay, could be any cycle. Let's suppose that I'm numbering it to B1 to Vn. Okay, something like this. Let's suppose B1 is the first node that either DFS or BFS is visiting in the cycle, right? B1 is the first node. Then BFS will do what? Okay, this is not the directed, this is undirected. Then BFS will do what? BFS will say that okay, I will go to the adjacent, right? So BFS will be going to the adjacent, which means BFS will say that I will, from this B1, I will go to B2 and Bn. This is what BFS will say. And DFS will say that this cycle will be in just one path, which means DFS will be saying B1, B2, B3 to Bn. Basically, if you are having a cycle, then DFS will create you a path, but BFS will create you a tree, something like this, right? So both will always be different. It's not just once or twice, or in some example. If it is a tree, then since it is just a one tree, right? It is just a one tree. You apply a DFS here, you apply a BFS here. You will be getting the same tree as it is. You will be getting same tree as it is, right? You apply anything. But if it is not a tree, if it is having a cycle, then you will always be getting the different answer. So basically it is a vice versa. If it is a tree, then both give the same answer. If it is not a tree, then both give the different answer. Not a tree means it is having a cycle. If graph has multi-edge, okay, multi-edge means you are having multiple edges. So why does this matter? I mean, okay, I don't think it will matter. You are having multi-edges, right? So you will just take one of the edge. I'm not getting your question. So how does this multi-edge make any difference? Okay. So this question, there has been quite debate on this question. Let's just see this question. This question is saying that you are basically doing what you, every of the program is doing what the same, almost same thing, but there is just a difference in free, right? So this is the P1 and P1, P2, P3, almost everyone is doing the same thing. This is P2 and P3. So what they're saying is that you are having you are calling this foo, and this foo is having one local variable which is a. Now you're passing the value to the local variable, and then this star destination equal to star source. This is bit confusing you, right? This has nothing to do with the memory leak. I mean, see, it is just a memory implication. You are saying you have one memory from the heap, which destination is pointing to, right? There is a memory from the heap which destination pointing to. Star DST will just make this memory as 3, or whatever you are passing, the a equal to 3. So it will be star source, means it will just assign the 3 here. It has nothing to do with the memory leak. Nothing to do with memory leak, right? Okay. So Dangerous clearly is saying that multi-edges matter. So in that previous question, I'm not able to think that why multi-edges will matter. I mean, even if it is multi-edge, okay, they will. You are saying they will take the different edge. That's what you are saying, right? I mean, I'm not labeling any edge, right? I'm not labeling any edge. So both edges are identical to me. I'm assuming that even if they are multi-edges, then both edges are identical to me. It is just connecting A and B. Okay. Otherwise, generally, we never think about the multi-edges. I mean, we never have to think about it. They will, if that is the case, they will definitely give you. Cool. Is this clear that this thing will not be having any impact on the memory leak? So I'm doing what, just for the analysis purpose, I'm just removing this, right? Now what this is saying, that you are saying that there is a memory that you ask from the heap, and then let's not worry about the assignment. This is just assigning. Okay, I mean, you are assigning 3, that's okay. Then you will return that particular address to here. Now here this B will also be pointing to the heap. Now you are returning star B, that's fine. So here P1 is not having any problem. But if you are freeing this up, which means you do not have this as a valid memory, you are freeing this up, then you are returning. Now B is also pointing to invalid memory. So here in P2, B is also pointing to invalid memory, then star will be a dangling pointer, right? So P2 is dangling. Now P3 is saying that you are not freeing this up, good. So you're freeing in B. So P2 and P3 are identical. It's just you're freeing it here or you're freeing it here. So if you're freeing in foo or you're freeing in this P2 does not matter. Like ultimately you're doing star B. So that's why P3 is also a dangling pointer. Right? P3 is also dangling pointer. There is no memory leak in P1, P2 and in P3 because in every of this program, sorry, P1 is having a memory leak. P1 is having a memory leak because I'm not freeing up. But P2 and P3 does not have memory leak. They both are having dangling pointer, right? They both are having dangling pointer. P1 is having a memory leak. Okay. Now this question was also nice question. Here we are saying that how you can resolve the conflict manually. So basically, if you are here, let's suppose if you are in state 5 and since it is SLR1, it is having, let's suppose I have helped you to draw the parsing table. Otherwise I could have not given the parsing table, but it will be too lengthy to not give the parsing table. That's why I have helped you with the parsing table. So they are saying you have two options here, right? I mean here, if plus comes, then either you can go here, which means if plus comes you can shift this dot. Okay, so let me just tell you what you are having in the state 5. So see here, let me remove unnecessary things. So in state 5, if plus comes, then they are saying that you have two options. One is that you reduce e plus e to e, right? I mean there is one reduction that you can do on the plus. Okay, if it is LR0, you will be doing this reduction everywhere, but if it is SLR1, you will be doing based on the follow. But they have given you to they have helped you with the parsing table, so you do not need to worry about that. Okay, what is the follow and all? They have already helped you with the parsing table. Now what they are saying, that if plus comes, okay, so if plus comes, then in the 5, if plus comes, then either you can shift this plus, which means you can go here, or you can reduce this to e. So if you want to say that, okay, you want to give the left associated to the plus, you will be definitely going for the reduce, right? Because you want to do this e plus e first. You want to do the whatever you have seen, you want to do this plus first. So that's why you will be doing this one first. Dangerous Clady saying how P1 is having memory leak. I don't know why this problem is difficult. Literally, I'm very much surprised. Where is the free you are having? Clearly, it is a memory leak. Where is free? You're not freeing up the memory, and then when you comes to the main, you're just losing that memory access. No, you just see the main, right? P equal to null. P equal to null means whatever this foo is returning, you are losing that access immediately. That's why I'm saying like main is something like this. Okay. So it was very easy question, to be very honest. It should not have taken more than 1 or 2 minutes. So if you want to really have give the plus left plus as a more priority, which means you want to make the plus left associative, just reduce it, right? Now at 5, similarly, if multiply come, then you can go to some state, or you can reduce this, right? So what you will be doing will be, on the multiply you will be taking this reduction, or you will be going some state, let's suppose state 4. Obviously you will be going to some state, because if you reduce it, you are going the more priority to plus over the multiplication. That's what you should not be doing. So that's why you should be going to the next stage. So basically on multiplication you have to do the shift. On the multiplication you have to choose the shift, and you just remove this. On the plus you have to reduce it, because you want to make it left associative, you remove this. So basically this parsing is just one simple algorithm that you will be writing in C programming or something, right? So you can do manual resolution, even though the algorithm, even though the grammar is ambiguous, but you can do the manual resolution. Okay, cool. Yeah. So let me know if that question was clear to everyone. This was OS question. That was an easy question, I think, right? I mean, they are just assigning. If it is even, it will be stuck. If it is odd, then only it will run, right? So it was also a nice question. Let me know if you were able to do this question. You want me to solve this question? Okay, no problem. If you have forgotten to see main, that's not an issue. Let me know if that is fine. This question, should I solve it here or you have already solved it? Okay. Yeah. So let's do this question. It was very nice question. Let's just do this question. What they are saying that you are using two level paging, which means, what does two level paging means? That you have one page here, which is outermost page, and each entry is pointing to one of the page, right? Have you seen my OS PYQ series? That is very nice series. I will say, like, I have put a lot of efforts to create that series. So have you seen that OS PYQ series on YouTube? OS PYQ YouTube series. Let me know. So there I have explained this multi-level paging in a great detail. So this is the outermost. This is pointing to one of the page. This is pointing to another page, something like this, right? And then this will point to the physical frame. I mean, it will actually point to the physical frame wherever you have stored, right? Now they are saying that some of the entries are valid, some of the entries are invalid. Now the leftmost bit is one, then they are saying it is a valid, right? The structure they have given, the valid bit, and then followed by the physical frame number. So if it is one, then it means then the hexadecimal it will be more than 7. It will be at least this 8, or maybe this is 9, right? Maybe 10. Either 8, 9, 10 means A, like that, right? So it cannot be 7 first of all. So it cannot be 7. So that's why this is not a valid. This is 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 valid. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, and this 8, right? So 8 are valid and others are invalid. Now, if 8 are valid, what you will be doing? You will be saying that here 8 entries are valid. 1, 2, any of the 8 entries, right? Let's not worry about it. So it means that 8, it is pointing to 8 pages. So basically, there are 8 valid pages, right? I mean, if there are 8 valid entries, then there are only 8 pages you need to store here, because other pages are not necessary to store, right? We need to store. So with multi-level paging, you are storing one page here and 8 pages here. So total you are with two level paging, you are having 9 pages. But if it is flat, see, flat doesn't mean that the number of pages will be lesser here. See, the total number of pages, if these are the 8 entries that I have, sorry, these are the 32 entries that I have, then the total number of pages in the flat will be the 32 pages, something like this, right? Will be the 32 pages. Here you already have 32 pages. Now, if you are just using the flat level, then it means you are not having the indexing. That's all. But let me ask you, do you change this 32 pages in the flat? See, initially it was that. Then you said like, okay, this is valid, this is valid, this is valid. So I just need to have 8 entries, right? I just need to have 8 entries here, and then I just don't store it, right? Don't store it. So that's where you are saving the space. If you're not storing, you are saving the space. But in the flat, since everything is just one page, right? Because it is a flat, everything is just one page. You have to store everything. So that's why the total space taken by the flat is 32 pages, right? So here the total space taken by the two level is 9 pages. Total level taken by the flat is 32 pages. So 32 minus 9 is 23 pages savings you are doing. Right, one page size is given, so you can calculate the answer. Let me know if there is any confusion here, because that question has been asked multiple times in GATE. Okay, in fact in GATE 2021 that question has been asked, and there has been many times that these kind of questions have been asked, that how does multi-level paging save the space. Okay, so this is basically related to how does multi-level paging save the space. Let me know if this concept is clear to everyone. Okay, so this question we have solved in the marathon itself. You can watch that video. We have solved in the marathon. You can watch that video from that, right? That question was very nice. Like, once you understand the concept clearly, let me know how many of you have watched the CN the session 1 in the marathon. There I explained what is data link layer, how does this stop and wait and sliding window protocol behave. Okay, let me know how many of you have watched the CN marathon one. CN one. One means first part from the marathon for the CN. Okay, that was very nice question, extremely nice question, one of my favorite question I can say, right? So let's just solve this question. Yeah, actually, to be honest, after going through all the questions, I think the questions are little conceptual. I mean, every question are having some concepts. So maybe Deepak has put the questions which are, I mean, which are less tricky than the question that I put, because we wanted to make the paper balanced. So maybe I just realized that all the questions are little bit nice. I mean, you cannot do it without thinking much, right? I mean, you have to think through the questions in all the questions. Okay, thank you, Vijay. Thank you, Shyam. Cool. So that question was very nice. I have given the answer, but let me just again tell you. Suppose out of this question, suppose suppose instead of this question, I just ask you one very simple thing. Let's suppose you are in your home. Okay, maybe my home is in Jaipur. Let's suppose I am in Jaipur. Now there are some probabilities that I go to some place. Let's suppose I go to Chennai with probability 1 by 3. I go to let's suppose Bangalore with some probability which is 1 by 4, and then I go to maybe Hyderabad with some remaining probability whatever it is. Let's suppose this is 1 by 3 plus by 4, it will be 4 by 12, 3 by 12, 7 by 12, right? So it will be 5 by 12, I think. Okay, so suppose with this probability I go to Hyderabad. Now from this Chennai, I'm going to two places, maybe by 1 by 2 probabilities. I'm going to place, let's suppose, not Madras, Madras and Chennai are same. So let me just say maybe Bhopal. I'm going to Bhopal. Here I'm going to Indore. And from this Bangalore, with 1 by 3 probability, I go to Indore, and maybe with some probability, 2 by 3 probability, I go to some other city. Similarly, with some probability, from this Hyderabad, I go to Indore, let's suppose with some probability which is 2 by 3 probability. With 2 by 3 probability, I will go to Indore. Now tell me, what is the total probability that I go to Indore? What is the total probability I go to Indore? What you will say? You will just sum up all the probabilities, because this is one way, this is one path, this is another path, this is another path. So whichever path is leading to me Indore, you will just sum up all the probabilities, which means 1 by 3 into 1 by 2 plus 1 by 4 into 1 by 3. This is another path, plus 5 by 12, 5 by 12 into 2 by 3, isn't it? So you will sum up all the probabilities. Okay. Niskarsh is saying, sir, could solve 85% of the question after mock, but not all during the mock, as all needed time. Yeah, that is fine, because that was just AIMT. I have put one of the post, if you see in our YouTube community post. Let me just tell you that what is the post that I have written. So there was one post that I have written today, just to address this. See, in that post, I have explicitly said one thing, which was this. See, I'm saying here that you might not have able to solve the question. Maybe you might not able to optimize those 3 hours, but thank God it was just AIMT, not GATE, right? I mean, see, those examinations that we are putting, either AIMT 1 or AIMT 2 or any of the mock, in those examinations you might do some mistake. Then you might realize that, see, our focus here currently, to be very honest, our focus is not to make you learn concept through the test. Through the test, we want you to learn the optimization thing now, right? I mean, concept is one thing that obviously will be the side way. You will anyway be learning the concept, but now you should be more conscious that you should be optimizing those 3 hours. So that's why, if you are not able to optimize in the 3 hours in those AIMT tests, that is fine, because it was just AIMT, not GATE. And let me tell you honestly, GATE will not ask you all of the question tricky. You pick any of the GATE paper, 50 marks question you can do. You can do in just basic understanding with some conceptual understanding. 50 marks question you can get. 50 marks you can get with just a little bit of basic understanding. So GATE will not ask all of the question that much conceptual. GATE is a beautiful opportunity. It will definitely respect your hard work. Okay. So don't worry if you were not able to solve. That is fine, because that was just AIMT. So in the GATE, just be careful about the time that you are spending for the questions. That is the idea. Okay. Let's just move to this question. Is this clear to everyone that how we are calculating the probability to go to Indore? Okay. Now here from this you can go to some probability to this node, you can go to this like with some probability to this node, and so on, right? Now what we can do, if I just ask you what is the probability that you could go to u again, then you just sum up all the path. Similarly, you go to you from u to y, right? Then you sum up all the path. So that's what we have done in the answer, I think. Okay, answer I have not written here, but I hope you understood, right? So if that is the graph that is given to you, if this is the graph, if this is the graph that is given to you, if I just ask that what is the probability that you go from u to y, then you just sum up all the path, right? Let me know if that is clear to everyone, or there is some issue in this. So you just need to all the path, you add all the path, right? Cool. So basically what you can do, like if I just ask you these two questions, which are these two, that suppose that you are at u and you want to come back to u, then what is the probability you come back to u? You just add all the probabilities and then you will be getting 1 by 2. You just add all the probabilities that you go out of the loop, which means you go to the y. So that is also the 1 by 2 probability. So finally you can say that whatever the control flow graph that is given to you, that control flow graph you can just summarize in this picture, which means you are saying that you go outside the loop with this probability, you go again to the loop with this probability. See, just remember this city examples, right? So you are going to some city, what is the probability? You just need to add all of the path, and not for the cities, anywhere you, if you are having multiple possibilities, let's suppose you do something with some probability with I mean, okay, that question also we have done the probability question, right? See, just a second. Okay, yeah, this question. See here, I'm having different paths to come to some situation where I'm at x equal to 0. So basically, there are different situations that are leading me here. So what I did, I just added all the probabilities of all the situations, right? If there are different situations that are leading me at some particular point, then I will be adding all the probabilities to come up with this particular situation. So if I'm coming from here, if I can also have this possibility, I can also have this possibility. So the probability will be the summation, right? Similarly here also, in the city example that I'm giving to you, okay, just a second, where is, yeah. So in this city example which I'm giving to you, so wherever from wherever you can come, you will just add all the probabilities. Similarly here, what I did, from wherever you can come to you just all the probabilities, and then you will be getting 1 by 2. Similarly, what is the probability to go to this by this by, then you will be adding all the probabilities, then you will be getting 1 by 2. So I can just summarize in this, isn't it? Now what we need to do, we need to just check that how to solve this question from now on. Okay, so Saurav is saying complete the marathon series. Yes, we will be starting the marathon series from today itself. We will be resuming it, right? So today most probably we will be having the probability marathon. Let me know if you have seen the linear algebra marathon. Have you seen the linear algebra marathon? So that there is one last lecture which is eigenvalue eigenvector. I have added that lecture in the playlist. You can watch that lecture because we do not have much time. So that's why we will be starting with the probability directly. Okay. Now what you can do for this question, you are saying that you are at u, you can come back to u with 1 by 2 probability, or maybe you can go outside. You can go outside with 1 by 2 probability. So what you will say that with 1 by 2 probability, I mean, you have already, since it is do while loop, you will anyway run it once. With 1 by 2 probability, you run it one more time, or with 1 by 2, then see with how much probability you run it one more time, with 1 by 2 into 1 by 2 probability, right? 1 by 2, see, let me tell you clearly. You are at u, right? I mean, you anyway did it once. You are at u, you anyway did it once, and now With 1 by 2 probability, you can go outside. With 1 by 2 probability, you can run, this is the probability, okay, run times. You can run one time. With 1 by 2 probability, you can run one time. Then, or you can say that with 1 by 2 into 1 by 2 probability, you will be running exactly one time, right? You will be running exactly one time. With 1 by 2 into 1 by, because with 1 by 2 probability, you will be running it one time, and then again, you are not running, so you go outside. What is the probability? You are running it two times. Okay. What is the probability that you are running two times? See, I actually, this method may overcount. That's only my concern. So basically, what I'm saying here, with 1 by 2 probability, you are running one time. Then if you want to run one more time, then also 1 by 2 again probability, right? Okay. So let me know if you are getting, or there is some confusion that you are having. See, what I'm saying, that you are at you go outside with 1 by 2 probability, you go again to u with 1 by 2 probability, right? This is the graph that I have. Now, you can say you are running one time with 1 by 2 probability, then, or you run it one more time, right? You run it one more time. So basically, the total times I'm adding it like this. You run it one more time with same probability. You run it one more time with the same probability, right? And then this will be an infinite series. You cannot say that you are running two times with, let's suppose, 1 by 4 probability or whatever probability, 1 by 2 square probability. Then you cannot add it to this number. See, there was one comment, and in the comment he was just doing something like this. With 1 by 2 probability or 1 by 4 probability, you are doing this, and then you are basically running it. Okay, let me tell you a wrong method, wrong way. See, you are at u, then you will be coming to you again with 1 by 2 probability. Now, tell me exactly one time you run it. What is the probability that you run it exactly one time? Okay, I mean, anyway, one you are running, but again, then you will be running exactly one time. You run it one time, and then you don't run it, right? You stop. What is the probability that you run it exactly two times? You will say exactly two times. You run it once, you run it again, then finally you stop. This is stop. So this is the probability that you run it exactly one times, and then since it is expected number of runs, it is asking into 1 plus 1 by 2 into k power cube into 2, right? So that's the way you can do it. But there is something wrong in this. Can anyone tell me what is wrong in this? You're running exactly one time with this probability, you're running two times with this probability, you're running three times with this probability. You can do it, but something is wrong with this. See, you cannot add it to find out the expected number of runs. Reason being is that if you're running two times, exactly two times, it already includes this, which is exactly one time, right? You cannot overcount it. Getting my point? So this is, if you are doing this, then you will be basically overcounting, which is wrong. Now that is why what you will do. You can do this in this way. You will say that you are at u. Let's not overcount, which means let's just forget about the past run. So you are running it one time with 1 by 2 probability, then again one time, and you don't count the previous one. Again one time with 1 by 2 probability, again one time with 1 by 2 probability. So basically, I'm not counting the previous runs here. I'm not adding the previous ones. And then since it is infinity, you will be getting just one here, right? Okay, if you add it, then you will be getting one. And then in this, I'm not adding the previous one. This is a fresh one, right? Again, you can run it with one time only, with one time 1 by 2 probability. Again one time with 1 by 2 probability. If you write it two and then you do something with these probabilities, then the problem here is that you will be getting the wrong answer because you are overcounting something, right? So that is the one way. Another way could be that we have solved these kind of questions in the goclass probability section. So another way could be, you are here, you with half probability, you will be going to the stop, you will be stopping, and with half probability, basically you will be saying that you are running it again, restart, I mean running again. Now if E is your answer, then you will say with half probability, you will be running it. So here, even if you are going here, you will be running at least one. If you're running again, at least 1 plus E more times, because if E is your answer, then E more times, because if there's a restart, then you have to just write E. Okay, plus this is just stop. With 1 by 2 probability you are running one time, with 1 by 2 probability you are running 1 plus E time. So this is 1 by 2 probability you are stopping, it means you are running at least one time. With 1 by 2 probability you are running 1 plus E times. What is this? How does this make sense? Basically it is called total law of expectation, that I have explained in the Go classes course. Maybe in the marathon also I will explain. Okay, so if there is an event A, then what is the probability of that event into even, which means if event occurs, then what is the expectation? If event doesn't occur, then what is the probability? If event doesn't occur, then what is the expectation at that point in time? Right? So that's how you can solve this question. Okay, cool. Let's move further. Yeah. So that was one question. I think that is okay. Everyone can do it. So yeah, that is all that I have. If there is any confusion, you can definitely let me know. Let me know how you like the questions. Like we have put some of the very nice question. We have put it intentionally. I mean, put it intentionally means like the questions are tricky, and we have put some easy questions also. It's not like that all the questions were tough. We have put some easy questions also. But I hope overall the experience should be the good, right? So overall you must have liked the experience. Let me know if this session is helpful. Just comment it out. If there is any confusion, then also comment it out. If it helped you in solving some of the questions, then also please let me know. So today I will schedule a probability marathon, maybe in the late night. I mean around the 8 or 9. Okay, around the 8 or 9 p.m. I will be scheduling, because I will just taking some rest. My I'm having a little cold, and then I will scheduling a marathon at 9 p.m. Okay, for the probability. So we will be having a probability marathon. Cool. Thank you everyone. Thank you so much. Let me know if there is any confusion. Okay. Let's meet at 9 p.m. Take care. Bye bye.